Thank you, Patrick. And I'd like to thank the organizers for inviting me to speak today. In fact, you know, I haven't really been working in Finsler geometry for a while, and so I wasn't sure what I would talk about when I was invited to speak. And in fact, my main motive was to come and find out what people have been doing in Finsler geometry in the last while. But there is one particular aspect of Finsler geometry that I find really interesting because it ties to my other main subject of interest, which is holonomy groups, and this is something that came up. In fact, when I first started doing this work, I was actually working on holonomy groups and not on Finsler geometry, and it only turned out later that it actually had something to do with Finsler geometry. But I'm going to present it today in the other direction. That is Finsler geometry, the problem that it corresponds to, and then how it turns out to be connected to holonomy. Let's see if I can do this. Yes. So the fundamental question, the way I'm going to pose it today, is what is the nature of the prescribed curvature equation in Finsler geometry? That is, if you in Riemannian geometry, we know the metrics of constant sectional curvature are well known. We understand those. They're completely determined locally. They depend on one constant, basically, the sectional curvature itself, and we know other things, like we know how to prescribe the Ricci tensor or various other aspects of partial differential equations. But in Finsler geometry, it's not so clear what the differential equations are and what they measure and how to solve them or how to describe their solutions. And so what I want to do today is talk about, in fact, what the equation of constant flag curvature is, or what its solutions look like locally and then globally. And my sense of local might better be called microlocal, because it's really talking about, and I'll say here, I'm going to phrase it in this term, although it will turn out to be relevant in the sort of global Finsler picture. That is, we start with a manifold of dimension n plus 1, and we take a hypersurface in, let's see, where is the, yeah, there it is. We take a hypersurface in the tangent bundle, which you should think of as the space of unit vectors for the Finsler structure. Yeah, there we go. Which you should think of as the space of unit vectors for a Finsler structure. But I'm going to take it in the generalized sense, in that the only thing I'm really going to require about sigma, other than it's a smooth hypersurface that submerses onto M, smooth hypersurface, is that in each tangent space, here's you have O of x, x and M, and in each tangent space, sigma represents a hypersurface in each tangent space that's locally convex, strongly convex towards the origin. I don't require it to be compact, although we'll see plenty of examples where it is compact, and I don't even require it to be globally convex. It could be something like this, for example, in theory. As long as it's locally convex towards the origin, the machinery works. Let's see. So the question is, what kind of geometry can you attach to such a hypersurface in the tangent space? And the theorem, which was basically due to Cartan, although in this form it's in Chern, is that there's a canonical ON bundle over sigma with a canonical parallelization of this bundle, such that all of the information about sigma, the way it sits inside M, can be read off from the ON structure on sigma. Remember, this ON, this is not strictly speaking just a Riemannian structure, although it implies a Riemannian structure, because sigma has dimension 2n plus 1, and this is ON. But be that as it may, what you get is, what you can think of is that the forms omega, the forms omega are semi-basic for the projection to M. They measure motion in the base manifold, the point space as people call it, and the forms theta 0j are also basic for the projection to sigma. Unfortunately, that shouldn't be a pi there. That should be some other letter, but in fact, that should be U, not pi. But anyway, they're U semi-basic. The omega naught, omega I, and the theta 0 I are U semi-basic. The theta 0 I measure how the unit vector moves. And then there are, in addition, the theta ij, which are skew symmetric, which are connection forms for this ON structure over sigma. The structure equations, as you write them down, that is, the differentials of the semi-basic forms can be written in terms of all the forms. They can be written in this form. I've written these two terms in red because these are the terms that don't exist when the Finsler structure is actually Riemannian. That is, these are the unit vectors of a Riemannian metric. These quantities, capital I, ijk, and j, ijk, are invariants that tell how the shape of the hypersurface differs from being an ellipsoid centered at the origin. This is the Cartan structure tensor, and these are the fundamental curvature invariants. The flag curvature, turns out the condition of constant flag curvature is exactly the condition that these terms are C. Constant flag curvature C is R 0I 0J is C times delta Ij. So that's the PDE. If you sit down and work out what it is in terms of the hypersurface sigma, these things depend on 4 derivatives of sigma. Which is a little bit surprising when you first think about it, because your intuition is to think that it depends on 2 derivatives, as it does in the case of Gauss curvature. Gauss curvature depends on only 2 derivatives of the metric. But in fact, when you sit down and compute what's happening here, when sigma is not an ellipsoid, the terms that are involved in taking these normalizations, you actually have you actually use the 4th order jet of sigma sitting inside Tm in order to compute these things. So prescribed curvature, even for a Finsler metric, prescribed constant flag curvature is even in the case n equals 1, that is on the surface, this is actually a 4th order equation for this hypersurface sitting in the tangent bundle. It's a determined equation when n equals 1. But when n is bigger than 1, it's more equations than there are unknowns, because basically sigma being a hypersurface in the tangent bundle, basically it's one function of 2n plus 1 variables to determine sigma. Now, these equations have an immediate consequence if you just plug them in and then differentiate these equations. One of the things that you get right away is that forces the R0 ijk to be 0, and so, which in the Riemannian case you would get, because of course in the Riemannian case, if you had constant flag curvature, that's exactly the same as saying constant sectional curvature, and then the Bianchi identities would get rid of those. But even without the ij, capital I and capital J being 0, these are forced to be 0 if the flag curvature is constant. And the fundamental question we want to discuss is how many solutions are there to these equations? And I'm going to consider them in the generalized sense. That is, I'm going to consider basically just a small piece of a hypersurface in studying what the equations are. But of course, we'll see that has consequences in the global picture. I'm also going to concentrate on the positive case. There's a similar story in the case c equals 0 or c equals minus 1 that is analogous in many ways, but for me the most interesting case is the c equals 1 case. And here's what the structure equations simplify to when you there's what became of the sectional curvature of the constant flag curvature, and as I said, the other r's vanish, and you still have the ijk and jijk. And one immediate consequence that you get from these structure equations, you can just read off, is that if you take the Rabe vector field on sigma, that is the vector field that's dual to omega naught, that is the geodesic flow vector field for the Finsler structure, then this quadratic form is actually invariant under the flow of E. That's not generally true, but it is true in the constant sectional curvature case. And I mean the constant flag curvature case, which is what we're going to consider always from now on. And what I want to do is look at the space of geodesics. But of course, in general, the space of geodesics may not be a manifold. But locally, you can always do this. So that is, by restricting to a sufficiently small neighborhood in sigma, you can always arrange that this Rabe vector field is geodesically simple. That is, if you look at the space of integral curves, then this space of integral curves has a Hausdorff manifold structure, so that this projection is a smooth submersion. The reason I call this Q is, as we'll see, this is actually, in the cases of interest, this is actually a quadric. It's actually a complex quadric, and so I'll call it Q. For example, in the case of constant flag curvature on the sphere, for example, the simplest possible case, this Q is exactly the space of oriented two planes in R n plus 2, and therefore it's the complex n quadric. It's a dimension 2n. Well, that connection with complex geometry is actually it actually persists even in the general case. That is, it turns out that this space of geodesics is not only naturally a symplectic manifold, which it always is, because the derivative of the Hilbert form is a symplectic form, is a non-degenerate symplectic form on the space of geodesics, but this symplectic form is actually compatible with this metric in the most possible, in the greatest possible sense, in that the pair of this metric and this 2 form actually define a Kähler structure on the space of complex structure, on the space of geodesics here. The proof is easy. It follows directly from the structure equations. If you take the semi-basic forms omega I minus by the way, whenever you see a Roman I, that means square root minus 1. The little script i's are subscripts. So if you look at this complex valued 1 form, I goes from 1 to n, then, for example, you can see that for zeta 1 times zeta 1 bar, that's exactly omega 1 squared plus theta 0 1 squared. And I over 2 zeta 1 wedge zeta 1 bar is actually omega 1 wedge, is actually minus omega 1 wedge theta 0 1. So the metric, which is well defined on sigma, is a quadratic form of type, a Hermitian form of type 1,1 with respect to these complex basis, and omega, capital omega, is of type 1,1 with respect to this complex basis.
The circle is symmetric.
Symmetric product, right? Yep. and that's of course the skew symmetric product. Now, the fact that you can do this is not so surprising. That's just algebra. But the interesting thing is that the structure equations, which were on the last slide, the structure equations actually, which gave the formulas for d omega I and d theta 0 I, when you combine them and just take d zeta I and expand it out, you find out that d zeta I is actually each d zeta is a linear combination of the other zetas. Of it and the other zetas. In particular, that implies that these 1-0 forms have the property that they're closed under exterior derivative, so the Neulander-Nirenberg theorem guarantees that there's an integrable complex structure for which these guys, which are defined up on F, actually span the pullbacks of the 1-0 forms. So there's a canonical, actual, literally integrable complex structure on Q, for which that's true. And moreover, capital omega, which is the 2 form, is of type 1-1, and by definition it's closed. So omega is closed, and therefore, because you have an integrable complex structure with a closed positive definite 1-1 form, this is exactly the data needed to define a Kähler structure on Q. And because this ties in with what I'm going to say next, I'll just remark that a Kähler structure is exactly the same thing as a UN structure that's torsion-free. That is, usually if you take a UN structure, you have to check 2 things in order to know whether or not you have a Kähler structure. You have to check whether or not the underlying almost complex structure is integrable and whether or not the canonical 2 form is closed. And those are exactly the conditions that we have here. I'll just remark, it's kind of an interesting fact, back up. It's an interesting fact that, for example, if the underlying manifold M were the M+1 sphere, and sigma is actually a genuine Finsler structure of constant flag curvature +1, then that has the property that all of its geodesics are closed, then in fact this Q is topologically the complex n-quadric. It's diffeomorphic to the complex n-quadric, and by a famous uniqueness theorem, there's only one complex structure on the complex n on that smooth manifold up to biholomorphism, and so in fact you're already frozen in the global picture. The complex structure is already frozen, so the only extra piece of data that this gives you is the Kähler form. And so it automatically is saying that in the global picture that we expect, there's already a huge amount of rigidity. Things have been reduced to a function on basically a perturbation of the standard Kähler structure on the complex n-quadric. That's in the case where the geodesics are all closed. Of course, they're not always closed, but globally, as we'll see, there are a lot of these that do exist. You can actually get a finer structure than just a UN structure, though, because it's not. And this is the thing that piqued my interest originally. If you look at this complex valued this Cn valued 1 form zeta on TF, then you'll notice that the kernel of zeta is exactly the vectors that go to 0 in the map from F to Q, because the omega I and the theta 0 I are semi-basic for Q. And so what that implies is that there is a unique map for any given f in little f in F. There's a unique map from the tangent space at Q of F to Q to Cn that makes this diagram commute. Call that V of F. That's what this red arrow is right here. So what this says is that the elements of F give rise to coframings on Q. In fact, they give a very nice set of elements in the coframe. They map this map from elements of F to coframings on Q that are compatible with the Kähler structure. This actually maps F into an open subset of an S times ON structure on Q. That is, sitting inside UN, there's actually a subgroup, which is the orthogonal group times the orthogonal n by n matrices times scalar complex scalars of norm 1. That's a well-defined subgroup of UN. It's equal to U when n equals 1. Of course, it equals U1. It's not a finer structure, but as soon as n gets bigger than 1, this is a much smaller subgroup than this guy. And so this extra SO1 times ON structure on Q, this reduction is a non-trivial reduction. Now, the one thing that you can prove, again, just from the structure equations immediately, is that this S1 times ON structure is torsion-free if and only if the original sigma is Riemannian. And remember, we're always assuming it's constant flag curvature, constant +1 flag curvature. And in other words, the only time this structure is torsion-free is when is in the trivial case, the flattest possible case of the standard n-sphere, the Riemannian n-sphere of constant curvature. However, as we're going to see, there's another way to enlarge this group sitting inside GLNC, and that's to enlarge the ON by making it be GLNR, and keep the scalars be unit complex scalars. And that's a well-defined subgroup of GLNC. And what we're going to see is that this underlying S1 GLNR structure is always torsion-free, no matter as long as we're in the constant flag curvature case. And this piqued my interest because this group, S1 times GLNR, sitting inside GL2NR, it acts irreducibly on R2N, but it's not on the accepted list of groups that can be holonomy of an irreducible torsion-free connection in dimension 2n. That is, there's a classification by Merkulov and Schwarzhofer where they're supposed to have a list of all the possible affine holonomy groups that can be torsion-free. It turns out this one's not on the list, and so in fact, when I was doing the calculations and I got to this point, I said, "Oh, these things are all going to be reducible somehow because the Schwarzhofer list says that they can't be irreducible." Well, let me take care of the case n equals 1, because in the case n equals 1 we don't get a reduction. There's nothing special to say at that point. But the case n equals 1 is already interesting because we do have another interesting structure here. In the case n equals 1, the picture looks like this. We have a surface, this generalized Finsler structure, which is a hypersurface, and the tangent bundle is a 3-manifold. The space of geodesics is 2-dimensional. We have the metric, which is omega 1 squared plus theta 0 1 squared. We have the 2 form, the area form, which is the Kähler form becomes the area form on this Q2. It's the integrability is trivial in this case, but there is an extra structure, which is something we haven't talked about. We haven't really used much. Is the Cartan tensor. And its covariant derivative and its E derivative, which is J. It turns out that this particular combination is invariant under is actually basic for Q2. That is, there is a 1 form on Q so that it pulls back to be this guy up on sigma 3. It's easy to compute. For one thing, it's semi-basic, and when you take its exterior derivative, you find out the exterior derivative is a multiple of this guy, and we'll see which multiple it is. So it's semi-basic, its derivative is semi-basic, so it's actually basic. The fibers here are connected, so there's actually a 1 form down here that's well defined. In fact, the structure equations tell you this, that if you take the Gauss curvature of this metric, then d beta is actually 1 minus the Gauss curvature times the area form on omega. And moreover, the following interesting thing happens. Every point of M2, if you look at its pre-image, is of course a curve. It's the space of the unit sphere, so to speak, at each point. And then if you look at the geodesics, the one parameter family of geodesics tangent through that unit sphere, whose velocities are those things in the unit circle, that gives you a curve in Q2. That is, you look at the pre-image of a point, it's a curve, push it down under L, it gives you a curve, I'll call it C of X, which represents the geodesics that pass through X. That's what sits in there. And it turns out, just following through the structure equations, it turns out that this curve is actually a beta geodesic. And what do I mean by that? If you take an oriented surface with an area form and you have beta as a one form on the surface, you say that a curve sitting in Q is a beta geodesic if its curvature times arc length is the pullback to the curve of beta. In other words, so for example, if beta is 0, then the zero geodesics are the same thing as just the ordinary geodesics of Q. The beta geodesics are defined by the property that their geodesic curvature at each point is determined by beta. This is and just as in the standard geodesic picture, through every point in every direction, there's a unique beta geodesic for any beta. So what this tells you is that the extra information that beta gives you is this family of curves sitting inside Q. This canonical family of curves sitting inside Q2.
Why this name?
What?
Why you call them beta geodesic?
Well, if beta were 0, they'd be geodesics. Yeah. So, some people call them magnetic geodesics. They think of beta as a magnetic form, and so this is how a geodesic particle would move subject to a magnetic field, right? Right. Yeah. Right. Okay. Just draw the picture again, and now there's a nice converse, which is this, that if you start with a surface, a metric, and its area form, and a one form that satisfies d beta is 1 minus k omega, and you take the unit sphere bundle of the metric, then sigma is foliated by the lifts of beta geodesics, and the leaf space of those beta geodesics actually, call it M, carries a canonical generalized Finsler structure of constant flag curvature plus 1. The point is that if you take this together with this structure equation and lift it up to sigma 3, you can now write down 3 forms on sigma 3 that gives a co-framing that exactly embeds sigma 3 as a hypersurface in the space of beta geodesics in such a way that it becomes a generalized Finsler structure of constant flag curvature plus 1. So in fact, this gives the micro-local answer about how many Finsler structures of constant flag curvature plus 1 there are in dimension 2. Basically, you get to choose a metric and you get to choose a beta that satisfies this one differential equation. Of course, up to diffeomorphism, a metric depends on one function of 2 variables, and a one form depends on it would depend on 2 functions of one variable, but we're specifying its exterior derivative, and so that cuts us down to 1 function of one variable. And so the data here locally can be thought of as 2 functions of 2 variables, and that actually gives the complete solution in this case in the micro-local picture. When n equals 1, the Finsler metrics of constant flag curvature plus 1 up to diffeomorphism depend on 2 functions of 2 variables. Now, So that's what the corollary is. And there's actually a global picture which says this: if you have such a structure satisfying this, and if all the beta geodesics are closed, then it comes from a global Finsler structure with constant flag curvature +1 on M2, which is a two-sphere. So the question is, can you find if you wanted to construct global Finsler structures on the two-sphere with constant flag curvature +1, what you'd want to do is find data like this that where all the beta geodesics are closed. Now that seems like a hard problem. In fact, we don't know all the solutions. We don't know what all the global solutions look like at the moment, but we do know a large class of solutions, which comes from the following result. Which is that if you take an oriented surface with a one form and a positive function on Q, you can always perturb it by scaling by L, scale the area form by L, and take beta and add the Hodge dual of d of the log of the square root of L, get a beta tilde. Then it turns out that the beta tilde geodesics with respect to this are the same as the beta geodesics of this. So this is a sort of a transformation of the data that doesn't change what the geodesics are, the beta geodesics are. And in particular, if you take a surface endowed with a metric and Gauss curvature, positive Gauss curvature with area form omega, and do this process, then start with beta equals 0. And a metric of Gauss curvature, and then this guy, and this guy actually satisfy the equation that the extra equation that we need in order to construct Finsler data. This again, it's just write out the structure equations, and so the corollary, the result is that if you start with a Zoll metric, so that's d sigma naught and beta equals 0, a Zoll metric has all of its geodesics closed on the two-sphere with its area form, and suppose it has positive Gauss curvature, then if you look at the space of oriented geodesics, then this data, d sigma squared is this, k naught times this, k naught times the area form, there should be an omega naught there, times instead of that, and beta is this guy, d log square root k naught, then this data is the data you need to construct a Finsler metric with constant flag curvature +1 on the space of geodesics, which is in fact a two-sphere. So in particular, since we know that there are lots of Zoll metrics of positive Gauss curvature on the two-sphere by theorem of Gilliman, that says that there are lots of Finsler metrics on the two-sphere with constant flag curvature +1. Basically, they depend on, this construction will give you essentially one arbitrary function of two variables worth of Finsler metrics with curvature +1 on the two-sphere. So, and they don't need to be real analytic or anything like that. The PDE, even the global solutions of the PDE don't need to have any kind of particular regularity. Okay, so I don't have a whole lot more time, but I wanted to explain what happens in the higher dimensional case, because we do have an answer in the higher dimensional case as well. From now on, I'm going to assume that n is bigger than 1. Again, I'll just recall the structure equations of the ON structure. It look like this, and it defines this S1 times ON structure on Q, and we have this isomorphism, this set of coframings on Q to Cn. The thing I was saying before is that although the structure equation gives you this, which says that the S1 times ON structure, these would be the connection terms for the S1 times ON structure. There's the ON connection, and there's the S1 part of the connection. But this term can't be absorbed in general because the IJKs are all symmetric in yeah, it's symmetric in ij and k. In general, you can't absorb that. So the S1 times ON structure has torsion. It's not a torsion-free structure. But as I was saying, if you define symmetric one form, sigma ij equals sigma ji equals sigma ij bar equal to this expression, which is clearly real and symmetric in I and j, then the structure equation, then this extra term can be absorbed as a symmetric term here, and now this takes values in GL and R. This if I combine the theta ij's, which are skew symmetric, and the sigma ij's, which are symmetric, this takes values in GL and R. And there's GL and R, there's the e to the I theta term, and this guy is torsion free. So, and because this S1 times ON structure for n bigger than 1 has at most, its first prolongation is trivial, this is the unique torsion-free connection for this S1 times ON structure. So you get a torsion-free structure sitting on S1 times GL and R structure sitting on Q, and geometrically, the picture that you need to think about as to what the extra corresponding data is if you look at now the pre-image under V of F of the real plane sitting in Cn, but the real Rn, that gives us a real n plane sitting inside the tangent space, and it depends only on the frame at the point. So what that means is that this S1 times GL and R structure defines actually an S1 bundle that is a circle of n planes sitting inside at each point, sitting inside the Grassmannian of n planes in the tangent space. That's what this R2 n plus 1 is. In fact, sigma, you can think of sigma is literally a circle of n planes sitting inside it, the fibers are circles in the tangent space here, and again, these n planes have the property that when you look at the images, that is the pre-image of a point is an n-dimensional submanifold. You push it down, you get an n-dimensional submanifold in Q2n, and these guys actually. These n-dimensional submanifolds are actually tangent to these n-planes. And conversely, if you take a connected n-manifold in Q whose tangent planes belong to this guy, then they're in fact it lies in unique CX. So this geometry of n-planes turns out to be the crucial thing that generalizes to higher dimensions, that carries the picture we want. In general, if you just have a S1 times GL and R structure, you still have this circle of n-planes sitting inside the complex of totally real n-planes sitting inside the complex n-plane. And I'll say that a torsion-free S1 GL and R structure is R integrable if every n-plane in R is actually tangent to an n-manifold, C, whose tangent places belong to R. Now, it turns out that when n is bigger than 2, any torsion-free GL and R structure on a 2n manifold is R integrable. And hence there is an n plus 1 manifold that consists of these n manifolds that tangent spaces belong to R. So you can reconstruct n plus 1. But when n equals 2, in fact, it turns out that there are other objects. Just say what the structure equations happen here. If you start with a torsion-free R integrable SN1 structure, the first structure equation looks like this. And if you differentiate these equations, you find out that d omega naught is of type 1,1. There's is real of type 1,1, where this is symmetric like this, and the curvature of the GLNR part actually looks like, well, the B's show up in two places, but then the RIJKLs show up as the curvature of this of the GLNR part. And I'm going to need the second Bianchi identity don't worry about the details, just look at the form of the equations, that when you take the exterior derivatives of the B's, there's the GLNR part of the derivative that tells you how the B's vary on the fiber. They transform like a quadratic form, like a real quadratic form. And their covariant derivative is this capital B corresponds to covariant derivatives. When you take the derivatives of the RIJKs, you get, again, they transform like a GLNR tensor, GLNR tensor, and then the covariant derivatives take this form. So the capital R and B are essentially the covariant derivatives of the little r and the little b. Now, if you stare at these structure equations, this is exactly the kind of thing that the Cartan machinery was designed to help you understand. If we have the derivatives of the omegas, the phis, and the zetas. We have formulas for their derivatives and formulas for the derivatives of the b's. There are so-called free derivatives, the capital B's and the capital R's, and we can now apply the Cartan machinery and compute whether or not these structure equations are involutive. That is, do these equations have solutions formally, and are the values of the functions freely specifiable at a point? It's actually stronger than that, but all I need is this calculation, and I'm almost done. The second Bianchi identity, which was just down at the bottom, the tableau for these R-integrable structures is involutive, and the Cartan characters are 0, the first two characters, then some slightly complicated formula for 2 up to n plus 1, and then 0 all past n plus 1. And according to the Cartan machinery, this gives you the result that up to diffeomorphism, the local torsion-free R-integrable S1 GLNR structures depend on n times n plus 1 functions of n plus 1 variables. And you can specify the curvature freely at a point. In fact, you can specify, subject to the Bianchi identities that you get by differentiation, you can specify the values of the little b's and little r's, the values of the big B's and r's, basically as far out as you want. You can specify the k-jet of a solution, and you can say how many different k-jets there are at any given k by looking at the structure equations. Corollary to that is that this group actually does occur as a holonomial of a torsion-free affine connection in dimension 2n. So there are lots of such structures. And that was the thing that I was interested in, was trying to determine whether or not this group could occur as a holonomial of a torsion-free affine connection. And because it was surprising that this guy was there, because it was, like I said, omitted from this classification. But now the interesting thing was, and it surprised me, was it turned out that these things actually are intimately connected with the Finsler structures, because if you actually start with one of these things, that is, you start with an integrable, a torsion-free R-integrable S1 structure with these structure equations like this, then if this matrix BKL, which transforms like a GLNR tensor, is positive definite, which they certainly exist because of the involutivity condition. If it's positive definite, then you can reduce to a S1 times ON structure by restricting to the locus where the Bij is 1/2 delta Ij. That defines an S1 times ON structure, F naught, and the structure equations. And if you now just separate out the complex structure equations into their real and imaginary parts and relabel everything backwards from what I labeled in earlier things, you actually get exactly the structure equations of a generalized Finsler structure with constant flag curvature +1 on the space of R leaves. So the end result is that essentially these S1 GLNR structures that have the B tensor positive definite, they correspond exactly to the microlocal GLNR Finsler structures of constant positive flag curvature +1. So there's so that holonomy problem actually turns out to be the same as the holonomy problem, and so as this guy. So the end result is that the space of the microlocal solutions of the equations for constant flag curvature +1 turn out to have the general solution depends on n times n plus 1 functions of n plus 1 variables. That's the takeaway. So there's lots of solutions locally. And there's also lots of solutions globally, by the way. I haven't talked about in fact, you can even impose the condition that the geodesics be projectively flat, and there's still lots of solutions. So lots of global solutions on the n-sphere. So we now know what they depend on. When we started out, it was some huge set of equations on one function of 2 n plus 1 variables, but now we understand what the space of solutions look like as something that depends on functions of n plus 1 variables, and this is a kind of it's appropriate for the finite dimensional integrable systems kind of picture, because what it says is that this system of equations is in some sense integrable. It's not immediately obvious that it would be integrable, but the geometry as you study it shows that there is a natural set of Cauchy characteristics in some sense that you can divide by and reduce it to a set of PDE that's involutive. Anyway. So I think my time is up, and I'll stop here. Okay. Thanks.
Thank you very much for this. Thank you very much for this last talk.
Oh, thanks.
Are there any questions? Yes.
So if you talk about microlocal
So, I think it's not on.
So if you talk about microlocal pictures, so you just mean you consider a small piece of this hypersurface sigma.
Right.
Yeah.
That's all you need to do the calculations. But if you want to get genuine Finsler structures, you need to consider global things. But the point that I was making is that we do have global constructions at this point. We know how to construct global solutions, but we still don't understand the full moduli space of the global solutions. We understand the local solutions, but not the global solutions.
And another question, so this generalized Finsler structure, they are, so in dimension 2 they're different, but in dimension larger than 2, these are actually the same as Finsler structures, or not?
No, you could have for example, there's nothing that stops there being a solution that looks something like this, where the solution, where the what do you call it? The hypersurface. The tangent indicatrix looks like it's not even globally convex locally. There's nothing that stops that.
Or maybe it's unbounded, or just exists. Right? Or maybe just unbounded.
Or just unbounded. Yeah, it could look something like this, right? Yeah. That is, the generalized solutions could look like that, yes. Right.
But is there not a theorem so saying something like that? So if you have an immersed, positively curved surface in Rn, then it is embedded.
Sorry? Say that again.
So I thought, so maybe I'm mistaken, but I thought so. There's such a statement, I think, by Gromov.
Oh, you're talking about maybe you're assuming completeness of something.
Maybe.
Yeah. You're assuming completeness of something and also some boundedness, because the paraboloid, for example, has non-negative curvature, non-negative affine curvature, and it's not bounded.
I want to say like compact.
Oh, compact's good. That's right. Yeah, but in dimension 2, of course, you can have this kind of thing, right? Yeah, but not in higher dimensions.
Right. If
That's
you add
correct.
compact.
Yeah, right.
Any other
Yes.
question?
So I again want to come back to your use of the word microlocal. Now it seems to me
Local in the tangent space.
local in the tangent space.
Right.
So precisely that.
Right.
Now, do I understand that on the geometric side, getting a microlocal solution to this system? Now this system comes out of just taking a piece of the manifold. Is the outcome thus that there's a smaller piece around the base point, which then acquires any one of these very large number of Finsler structures?
Well, there are various outcomes. I mean, you can, for example, you can show that you can actually get a genuine Finsler structure depending on n times n plus 1 functions of n plus 1 variables in a neighborhood of a point down in the point space. So there's actually there's a local statement. There's a local existence statement as well as a microlocal existence statement. But if you're just looking at the PDE itself, and the PDE can be defined purely on a microlocal Finsler structure, a generalized Finsler structure. That's what I call. And if you're just looking for the solutions of generalized Finsler structures, which is the first thing you'd want to understand is how flexible are the solutions, and then worry about global constructions and global rigidity. Then this answers the question locally. But there are global construction. There are local but not global general constructions. Even for the two-sphere, we don't have a. We don't have a full. We don't understand the full generality of even the Finsler metrics where all the geodesics are closed and length 2 pi. We have a large class, namely the Zoll class, but in some sense that's only half of them because that depends on one function of 2 variables. Right.
Any other questions? No. Just one. Is there any analog in higher dimension to the beta 1 form?
Right. So there is a tensor. There is a tensor that pushes down, which is the analog of the beta form. It's a cubic tensor, actually. There is a tensor that pushes down, but it doesn't contain all the information that you want to pick up the one-parameter family of planes. That actually turns out to be the critical object. Is this one-parameter family of planes of Lagrangian n-planes. Right.
And also, did you think about the question of having the curvature only sectional? You understand what I mean? The curvature depends on the direction. It's a flat curvature.
Yes,
if you say now the curvature only depends on 2 planes. It's intermediate between any curvature, problem, and constant.
Right.
Beta 1 form should play a role.
Right. Yeah. There are various prescribed conditions you could ask. For example, in the surface case, for example, the sectional curvature, the flag curvature depends on the direction, but you could ask that the flag curvature not depend on the direction, just depend on the 2-plane, right? And that's a PDE that's a weaker PDE than setting it to be constant. And we know what the solutions. We know how many solutions there are to that too.
Okay.
Right. Yeah.
No other question? Thank you, guys.
First of all, I will thank the organizer committee, invite me attend the conferences and give a lecture. The title of my lecture is On Finsler Surfaces of Constant Fleck Curvature. This is my abstract. This is the content. The one is a Finsler matrix, and the second one structure equation for a Finsler surface, and the third one Finsler matrix with a two-dimensional isometric group, and the fourth, 5, and the last one is the Finsler surfaces of the constant Fleck curvature with a Kelvin vector field. Okay, now we start. The first of all, I will introduce some definitions. A mixed norm. Now the mixed norm. Mixed norm on vector space V is a non-negative function from V with the following four properties. The first one, F is positively homogeneous degree 1. That means for any y belongs to V and any lambda is positive lambda, which satisfies this equation. F lambda y equals to lambda Fy. And the second condition is F is smooth on the V remove 0. And for the any tangent vector y, V remove 0. The following bilinear symmetric form GYUV is a positive definite. GYUV is defined by this equation. Now we can talk about the definition of the Finsler manifold. Let M is a differential manifold. Tm is a tangent bundle of the M. And a Finsler metric on the manifold M is a function, is a non-negative function with the following properties. The first one, F is smooth on Tm0. And the second one, for each point x, the restriction of the Fx is a mixed norm on the Txm because Txm is a vector space. So now we discuss some examples, important examples. The first example is the Riemannian. So we will introduce some basic formulas. If we suppose Gij is equal to F square over 2 y Hessel, then it is easy to check this formula. Square root Gij xy yij is equal to F. Here, x is the point of the manifold M, and y is the tangent vector of Txm. So, the first important example is the Riemannian metric. Riemannian metric F is defined by the this one. Just means Gij is depend of the point, independent of the tangent vector y. This is a Riemannian. So Riemannian metric, just Finsler metric, without quadratic restriction. And this is example of the Riemannian metric. This metric is defined on the unit ball because if the length of the x equal to 1, this is no meaning. So this is Finsler metric defined in the unit ball. This metric called the Klein metric. Bn means unit ball. And the second example of the Finsler metric is a locally mixed metric. What is a locally mixed metric? Locally mixed metric means the Gij just depend of the tangent vector y, independent of the x. For example, using the mixed norm on Euclidean space, we can define this locally mixed metric. And now we introduce another examples, rounded metric. Let alpha is a Riemannian metric, Aijx, Yiyj. This x is the point of the M. And beta equals to Bix, Yi is one form on the M. We can define the length of beta with respect to alpha. This is the definition of the length of the beta. If this one is less than 1, then alpha plus beta is a Finsler metric. We call this Finsler metric the roundness metric. In fact, this metric is defined by the roundness, physicist roundness. So we call this one roundness metric. For example, this F is a roundness metric. In fact, this one is a Klein metric, is a Riemannian metric, and this one is one form. In fact, this is a closed form and exact form. This F is also defined in the unit ball. We call this Finsler metric the Funk metric on the Bn unit ball. So this is a very good example. Now we go on the roundness metric. For the arbitrary constant vector A, constant vector A, we with the length of the A less 1, then we define this metric. This one just a Funk metric with plus this form, this form. We can show this one also a roundness metric. This is a Riemannian metric, and this one plus is a form. And which satisfies the condition of the Finsler metric. So this is the roundness metric. If A is a 0 vector, just the Funk metric. Roundness metric were first studied by the physicist G. Roundness in the 1941 from the standard point of the general relativity. So now we discuss the Finsler surface. At the beginning, we discuss the unit tent bundle and the index checks. Let F be a Finsler surface. The function F is determined by the set sigma. Sigma is a set of the xy belongs to the tangent bundle. X is a point, y is a tangent vector, such that fxy equal to 1. So, which is known as the unit tangent bundle because fxy equals to 1. So it is a unit tangent bundle. This is a tangent bundle, and the sigma is a unit tangent bundle because fxy equal to 1. For each x belongs to M, the intersection sigma x means equals to sigma intersect txm, the tangent space we call this one the index checks. Now we discuss the Hilbert form and the structure equations. Defined omega 1 equals to f yj dxj. This is a global differential form, one form in the on the sigma. The form omega 1 is known in the calculus of variations as a Hilbert form. On sigma, there is a coframe omega 1, omega 2, and omega 3. And with the properties that d omega 1 equals to minus omega 1 wedge omega 3, d omega 2 equals to minus omega 3 wedge omega 1 plus I omega 3 wedge omega 2, d omega 3 equals to minus k omega 1 wedge omega 2 minus j omega 2 wedge omega 3. Here I, j, k is the main invariant on the Finsler surface. I is known as the main scalar. We can show I equal to 0 if and only if the Finsler surface is a Riemannian surface. So we call this one main scalar. And the J is a Landsberg curvature, and the K is a Frege curvature. This is a generalized sectional curvature in Riemannian case. So this is the main invariant of the Finsler surface. Now we discuss Finsler surface has a constant Frege curvature. We suppose the constant Flag curvature equal to C. This is C. Consider the Finsler surface, which has a constant Flag curvature C. Differentiating the structure equation 2, 3, and 4, we obtain the following Bianchi identity. Di equals to j omega 1 times I2 omega 2 plus I3 omega 3. This just means j equal to I1. J equal to I1. And dj equals to minus ci omega 1 plus j2 omega 2 plus j3 omega 3. Just means j1 equal to minus ci as main I. I means main scalar. J means Landsberg curvature. Okay, now we discuss the orbit and the foliation. We suppose the Finsler matrix with two-dimensional orthotropic globe. Let MF be a Finsler surface and G is its orthometric globe. Then G is a least transformation globe. This is proved by the Professor Deng and Professor Hou in Nankai University in 2002. We assume dimension of orthometric globe equals 2. Consider the orbit of G as follows. Sigma xy equals to g hat xy. Here, the small g belongs to the capital G. G is the orthometric globe. The g hat, the g hat is left of the G, the small g, on the sigma. This is a unitary bundle defined by the g hat xy equals to g hat x and g differential y. Y belongs to the sigma x. Then the orbit of G forms a codimension 1 foliation gamma on sigma.
Why dimension 1?
Because the dimension G is equal to 2. Dimension G of equals 2. So the gamma's orbit form the codimensional foliation gamma.
Surface is two-dimensional.
Yes, that's right. Now we discuss the gamma. Well, we assume the gamma is determined by the non-zero one form, eta. Eta equals to u1 omega 1 plus u2 omega 2 plus u3 omega 3. That is eta t sigma xy equal to 0. On the sigma xy, we have g composite g hat xy equal to fxy. It follows that f restriction sigma xy equal to constant, and we obtain I and j are constant along the leaf of gamma. Hence, both di and dj is a multiple of the one form eta. This means di is this eta and also dj eta. This is mean. So continue. Together with 5, we have j equal to 0. Now we consider two cases. The first case is u1 equal to 0, and the second case u1 is non-equal to 0. In the case u1 equal to 0, we consider this equation. Then we have a j equal to 0. When u1 equal to 0, we can obtain the j equal to 0. J equal to 0, we can use the Abadadis equation. Abadadis equation, you know, is j dot plus ci equal to 0. So if the j equal to 0, we get j equal to 0, we get ci equal to 0. So if the c is non-zero, we can get the I equal to 0. I equal to 0 means the Finsler surface is Riemannian. And the c equal to 0 combined with j equal to 0, we can get, in this case, the Finsler surface is a local limit coefficient. Two case. So this case is very easy to classification. The one is Riemannian, another one is locally Minkowski. So in the general case, we can assume U1 is not equal to 0. Without loss of generality, we can assume that eta is equal to omega 1 plus U2 omega 2 plus U2 3 omega 3. Just we can assume U1 equal to 1. U1 equal to 1. As we mentioned as before, if the J equal to 0 implies that F is a Riemannian or F is a locally Minkowski. So now, from now, we consider the case J is not equal to 0. From the structure equation 2, 3, and 4, and Bianchi identity 5, 6, we have the following identity. The first one, J square plus Ci square equals to constant, and DU2 equals to CU3, and this is eta. And DU3 equals to minus U2 eta, and this equality. 1 plus CU3 square plus U2I, this is the main scalar, plus U2 square, and U plus U3J equal to 0. This is very useful. Just, I think, the Cardan test. This is Cardan test of the Finsler surface. And using 8 and 9, we have this equation. We can, that's du2 square plus cu3 square is equal to 0. And then it follows that u2 square plus cu3 square equals constant on the unit tangent bundle. This is a very interesting equation. Now, it turns out to be convenient to split the case into the C is positive, C is 0, C equal to 0, and C is negative. Moreover, by the scaling, we can reduce the three cases. The first case, C equal to 1, and C equal to 0, and C equal to minus 1. Just use the homothetic transformation. We can suppose we discuss these three cases. We mainly discuss C equal to 1, mainly. So now we discuss C equal to 1. We will find the normal form of the Finsler surface with a constant Frege curvature equal to positive 1 and 2 dimension, the isometric globe. In this case, C2 square and U2 square and U3 square is a non-zero constant by the 11 and 10. So we can assume C2 square and U2 square and U3 square equal to 1 over R square, where R is a positive. Right now we write U2 equal to 1 over R sin t, U3 equal to 1 over R cosine t, where t is a function from the unit tangent bundle to R. By 8, 9, and 13, we obtain dt equal to omega 1 plus 1 over R sin t omega 2 plus cosine t omega 3. Now we find the constant s. Plugging 13 and 10 plus 13 into 10, we find this formula. This means this one is equal to this vector I plus R plus 1 over R sin t and J plus R plus 1 over R cosine t is proportional R cosine t minus sin t. So this vector and this vector is proportion. So we can suppose there is a S in here. The S is a function from the unit tangent bundle. And then we can prove S actually is a constant. The 15, the formula E15 is equivalent to the following. I is equal to this one and J equal to this one. Because this one is SR cosine t. And the second component is equal to the SR minus sin t. So we can get these two equations. So we get the main scalar is equal to this one, and the Landberg curvature equal to this one. And together with 7, the formula, we can show the S actually is a constant.
So why is this a constant?
Just use these two equations and 7.
What is 7?
Okay, just wait a minute.
It's hard to follow when you jump in.
Use this one. We substitute this one. Yeah, we can get this constant. Yeah.
Okay.
This one. Yeah. Now we will find one alpha and one form alpha and the positive function a. Now, substituting 16 and 17 into the 3 and 4 yields these two equations. Now we define the alpha, the one form, which is equal to cosine t plus s sine t omega 2 minus sine t minus s cosine t omega 3. We can show the omega alpha is a closed form. In direct calculations, use d alpha equal to this one. Here, the term 1 is defined by this, and term 2 is defined by this. Then we substitute 1 and 2 into this one. We can show this d alpha is closed. Just means d alpha is equal to 0. Plugging 23 and 22 into 21, we obtain that one form alpha is closed. It follows alpha is a locally exact differential form because a closed form locally is exactly. So locally there exists a positive function a such that alpha is equal to 1 over Ra dA. Now we find one form, define a one form beta and a function b. We define the beta equal to 1 over a and sine t omega 2 plus cosine t omega 3. Then we can differentiate the beta by this one. Here, the one term defined by this one, and the second term, two term, defined by this one. And then we substitute 1 and 2 into this formula. We can show d beta is equal to 0. That means beta is also closed. So beta is locally exact form. Substituting this one, we can obtain d beta is equal to 0. So beta is closed. And it follows locally there exists a function b such that beta is equal to r dB. By 29, we have dA wedge dB is equal to omega 2 wedge omega 3. So this dA and dB is independent. Combining this with 14, we get dt wedge dA wedge dB equal to omega 1 wedge omega 2 and wedge omega 3. This is the volume element of the 10 unit bundle. So it's not equal to 0. So we conclude ABT is a local coordinate system on the 10 unit bundle sigma. So we can solve for the omega in the form. This is the normal form of the Finsler surface of constant Frey curvature 1 with a two-dimensional isometric loop. This is a normal form. Just means omega 1 equals to dt and minus a dB, and omega 2 means equals to this one times dA plus this one times dB, and omega 3 equals to this term times dA plus this one times dB. So the 13 is a normal form for a Finsler surface with a constant Frey curvature 1 with a two-dimensional isometric loop. This is a normal form. It depends on two constants. One is R and another one is S. Depends on two constants. So we conclude the theorem 4.1. The space of the Finsler matrix of constant Frey curvature 1 with two-dimensional asymmetric globe depend on two arbitrary constants. The first one is R and the other one is S. Now we discuss some reconstruction. Reconstruction means if we get we take the arbitrary constant R and S, we reconstruct a Finsler surface, which has a constant curvature 1 and two-dimensional asymmetric globe. Now we begin. Yeah, let E be a Libel vector field of F. Then we can conclude omega 1E equal to 1 and omega 2E and omega 3E equal to 0. Together with this formula, we get dAE and dBE equal to 0, dTE equal to 1. It follows E equal to partial and partial T. Equivalently, T curves are the follows of E. This is just a geodesic of the Finsler geodesic. And a curve is the definition. The curve is a unit Finsler speed geodesic if its canonical vector in the sigma. Sigma means that unit tangent bundle is the integral curve of the E. This E is a Libel field. This is follow the paper of the Professor Bryant. Thus, the T curve are the canonical left of the unit geodesic on MF. That is gamma. We suppose gamma is the set of the canonical left of the unit speed geodesics of MF. Small gamma T equals to ABT. AB is a constant, T is a variable. It follows that AB is a local coordinate system of the gamma, of this gamma. Now we discuss the new local coordinates system on the unit tangent bundle. Setting x1 is this one and x2 is this one. Here AB is a constant. We see that dx1 is satisfy this formula, and dx2 satisfies this formula.
What? I forgot what is P of T.
T is a variable. D.
In x2 you have P of T over A.
Oh, D is a derivative.
Formula 32.
X2.
32?
What is P of T?
P of
Oh, PT. PT is a function. A function is just one variable function.
It's an arbitrary function.
Arbitrary, yeah. Then we will solve this function.
Later we'll
Next we will solve these functions. Yes. Thank you. From the 34, we have the dx square equal to 0 mode, the omega 1, omega 2, if and only if the P satisfies this ordinary differential equation. 33 and 32 implies that dx1 wedge dx2 wedge dxt dt equals to this one, because ABT is independent. So if the t is not equal to 2 pi k plus pi over 2, then this one is not equal to 0. So x1, x2, and t is a coordinate. In particular, we obtain that dx1 wedge dx2 is non-equal to 0. Thus, we get the span dx1 and dx2 is equal to span omega 1 and omega 2, where pt is a solution of the 35. P is a solution of this ordinary differential equation. So we conclude x1, x2, t is a new local ordinate of the system on sigma. Here, x1, x2 is a local coordinate system on the M. By the 36 integral curves of the FAP equation, omega 1 and omega 2 have the following form: t to the x01, x02 t. Note that the integral curves of the equation omega 1 equal to omega 2 equal to 1 is precisely the index checks. Hence, this equation note the index checks of the MF. It follows that this is a set of the index checks of the MF equals to IT equal to x1, x2, t. Here, x1, x2 is a real number. We know there is a bijective mapping between the index checks and the point of the MF. And therefore, x1, x2 is a local coordinate systems of MF. So now we recover the Finsler metric from the substituted two constants. From the 31, we get the local coordinate system ABT, gamma t, A0, B0, t, is a canonical left of the unit speed geodesic for each fixed A0, B0. Together with 32, we have the in local coordinate system x1, x2, t are the canonical left of the unit speed geodesic 38 is given by the gamma tilde t. Gamma tilde t satisfies this one. Projecting gamma tilde to m, we obtain the each unit speed geodesic of f is given by this equation, gamma hat. For the constant A0 is bigger than 1, is positive, and B0. So it follows gamma hat derivative t is equal to this one, since the gamma hat is a unit speed, so we have the speed is equal to 1, and so this f is equal to this formula. It follows the Finsler metric f equal to x1, x2, y1, y2. This x1, x2 is a point, and y1, y2 is a tangent vector satisfied by this formula. Because partial f partial b is equal to 0, so we can rewrite this formula by this one, where x1 and x2 is given by the 32. It follows partial x2 and partial b equal to 1, and it follows that partial f partial x2 equal to this one and equal to partial f partial b equal to 0. Thus, f is independent of the x because this one. So x is independent of the x. Suppose f satisfies the x1 equal to this one, and y1 over f satisfies this one, and y2 over f satisfies p prime t over a, where pt is a solution of the ordinary differential equation 35. Then f satisfies this one. Combining the 40, we obtain the 39. Thus, we can recover the Finsler metric by eliminating a and t from the 41. So now we consider some interesting case, simple and interesting case. The s equal to 0. In the general case, it is very difficult to find the equation of this ordinary differential equation. In the simple case, if s equal to 0, we can solve this ordinary differential equation. Let us take a look at the special case when f is equal to 0. Then the ordinary differential equation can simplify this one. Now we discuss some proposition 4.1. Assume that f x1, x0, 2, y1, y2 satisfy this equation, where the phi is given by the phi z defined by r square z, and the psi z minus 1 plus z2 square r square over 2, and psi satisfy this equation. Then the 41 holds 41. Where is 41? 41. 41 is here. 41 is true, is holds. If and only if 41 holds. In this condition, then 41 is true. Where PT satisfies 42. PT satisfies this ordinary differential equation. Okay, now we can give some example. Reconstruction is a very special case. Suppose S equal to 0, R equal to square root 2. Square root 2. 45 simplifies the psi prime z equal to 1. It has a solution psi z equal to z. Together with the 44, we get the phi z equal to z squared minus 1. From 4,3, our Finsler metric F satisfies this equation. Just simplify this equation. This is a very simple the equation. So we can get the solution. The non-negative solution is given by this one. Hence, F is a singular round metric. This is a Riemannian metric, and this one is a one form. Because F x1, x2, 0, 1 equal to 0. So F is a singular. Yes, a singular. Because in this vector, F is equal to 0. For the regular case, F is non-zero. So
So it's at every tangent, at every point of the manifold, there is a point where F is
the manifold now is R2. The Finsler surface is on the R2. This is the point. Then this is the vector. In the
x1, x2, right?
Yeah. The point x1, x2.
So it is not negative still. So there is a 0 points, but it is not negative otherwise, right?
Yes. Yeah,
So,
you're
but
right.
what is the curvature? It is positive or it's 0 curvature?
The curvature is a positive 1.
I mean, I really doubt that it could be correct because we know that in the Randall's case, the curvature is constant only if you have the terminal transformation with respect to some Killing vector field, and you don't have Killing vector field of constant length in the surface case, in the curvature which is not non-zero.
Yeah, in this case, the curvature is positive.
Yeah,
Positive.
but then the
Positive.
Killing vector field you use for terminal transformation should have constant length because it is pass through 0.
Because this is a generalized Finsler surface, not regular, generalized. Just before the Robert Blunt says this one, generalized Finsler surface, not the regular. This is a generalized Finsler surface. So in the some direction, F can equal to 0. Yeah.
But this is only one direction, right?
Yeah. Yes. Just means in the regular case we F x y. If y is non-zero, this is the positive.
Yeah.
But in our case, F x1, x2, then 0, 1 is equal to 1. So this is a singular.
Is 0, 1 a Killing vector field?
Yeah. So this is singular because this is not satisfy this one.
Is 0, 1 a Killing vector field? 0, 1.
Yeah. 0, 1 means this is not equal to 0. The vector not equal to 0.
If you take the Killing vector field as coordinates 0, 1, is it Killing 1?
D over dx2, right?
D
Yeah.
over dx2 is Killing field?
Yeah.
Yeah, but then it must have, but then it has constant length because it's 0. And you do have constant length Killing vector fields on Riemannian metric of constant curvature different from 0.
This is a positive constant curvature. This example. We can discuss more, maybe in this afternoon. This is a singular, because in the direction 1, 0, 1, this direction is this one. Just 0, then dx1, and plus 1, then dx2. In this direction, the f is equal to 0. So this is a singular. In this direction. So this is a singular. So this is, we discussed the generalized Finsler surface.
Can you make a picture of indicatives at one point of this guy, of this F.
Oh.
Is it sphere? Is it
Parabola probably.
Yeah. It's parabola, yeah?
It has
Maybe.
null direction. It has some null direction.
Yeah, this is X direction. In this direction is singular.
So can you make pictures
Non-compact.
indicators of this F?
It's not compact.
It's not compact, yeah?
Something like parabola.
So,
Or maybe-
Vladimir, maybe you're right. The length is constant. The value of this length is 0.
Yeah. Okay.
Your Killing field has 0 Finsler length. So maybe it's not controlled. Although I'm not sure.
Maybe we can discuss this one tomorrow afternoon. Yeah, tomorrow afternoon. This is singular. Another example is we suppose s equal to 0 and r equal to square root r, 2 kappa. Here kappa belongs to 2, 3, and 4, and so in this case we can give many examples. Then 45 implies psi prime z equal to 1 plus z square square kappa minus 1. It follows that psi z equal to the integral 1 plus z square and kappa square kappa minus 1 dz. And therefore psi is a polynomial of the degree 2 kappa minus 1. Combining with the equation 44, we obtain the phi z equals to the 2 kappa z psi z minus 1 plus z square kappa is a polynomial of the degree 2 kappa. Thus, our Finsler metric f satisfies the polynomial equation of the degree 2 kappa. In the special case, kappa equals 2. Now we discuss this one, kappa equals 2. Let us look at the special case when kappa equals 2. Then psi z satisfies this formula and phi z satisfies this formula. Together with the 43, we have y squared over f equal to minus x1 4 times 4 and this one and this one. And simplify this equation, we get the f equal to this one. Here x1 x2 is a point. y1 y2 is a tangent vector. Here a is defined by this one. Here b is defined by this one and c. In the direction y equal to 0, 1, ABC is equal to a equal to 3, b equal to 0, and c equal to 1. Therefore, f is equal to 0. Hence, f is a singular metric, Finsler metric, which is a singular in the direction y 0 and 1, just the before case. So also is a singular Finsler metric. Then we discuss the c equal to minus 1. In this case, we have the similar calculation. We can get the normal form.
Sorry, c equal minus 1 means the curvature is minus 1?
Flat curvature.
Flat curvature is minus 1.
We just discussed the minus 1 because we can use the homothetic transformation.
Yeah, okay, no, just...
Yeah. In the general case, it's similar. Yeah. This is the normal form of the Finsler surface with a constant curvature equal to minus 1 and 2-dimensional isometric slope. So we get the following theorem. The space of the Finsler metric of the constant curvature minus 1 with 2-dimensional isometric slope depend on the 2 arbitrary constants. The one constant is r, and another one is r, another one is s. 2 constants. This is minus one case, and this is how to reconstruction from the 2 constants. The one is r, and another one is s. Reconstruction. This is reconstruction, just similar to before. This is reconstruction. We can give an example. Suppose r is equal to 0, s equal to 0, r equals square root 2. Also, we can find the ordinary differential equation. Solve this equation, we can reconstruction Finsler's surface, Finsler metric, which has -1 constant Frank curvature and 2-dimensional isometric globe. Now the second case is C is equal to 0. The normal form is C equal to 0 is by this formula. So we can get the next theorem. The space of the Finsler metric of constant Frank curvature 0 with 2-dimensional isometric globe depend on the two arbitrary constants. The one is S, another one is R. Now the reconstruction. So the next one is the sixth, last part. The last section we discussed the Finsler surface of the constant Frank curvature with a Killing vector field. This is a joint work with Professor Bryant. The normal form, in this case, the normal form, if the constant curvature equal to positive 1, C equal to 1, we can get the normal form in this case. Here, the U and V is a function, just a one variable function. So we can conclude this theorem. The space of the isometric classes of Finsler matrix of constant Frank curvature 1 that admits a Killing vector field depend on two arbitrary functions of one variable. Here, two arbitrary functions. The one is a U, and another one is V. Just U equal to UA, V equal to VA. And the second, C equal to 0. This is the normal form.
To follow, when you had two Killing fields.
One Killing field.
No, but previously, just to understand the grand issue, when you had two Killing fields, the two parameters are constant. When you have only one Killing field, now the parameters are functional parameter.
Yeah.
Much richer class.
The two Killing vector field, if the independent of two Killing field, just before I said the two-dimensional isometric group. This is something.
No, exactly.
Yeah.
So then in this case, you have two constant parameters, two constant.
Yeah. In two Killing fields.
And now it's two functional modular.
Yes. Two functions is one variable, two functions. In the general case, just the first talk, Professor Bryant said in just the constant curvature equal to 1, the surface. This is a two function and two variables function. Yeah.
But if you have zero curvature, why you have only two numbers to specify? Because you can choose Minkowski norm at one point and translate it everywhere by parallel translation. You would get something with zero curvature, and still we have the Minkowski norm to be arbitrarily chosen. Say again? I mean, if it has two Killing fields, try to do it on flat.
Yeah, but I think so. These are the normal.
他说太快了，我喝点水。
So J's or I's should be non-zero.
So it's microlocal, yeah?
It's non-Minkowski.
Okay.
Yeah, okay.
Okay.
UI equals having taken care of in some early pages.
Okay, thank you. So this is a case of the C equal to 0, the normal form. And then the C is negative. C equal to -1. This is the normal form of the C equal to -1. So we get the following result. The space of isometric class of Finsler matrix of constant Frank curvature equal to -1, which admits a Killing vector field depend on the two arbitrary functions of one variable. the one function is u equal to ua, and u, and another function is v. Two functions. One is u, and another one is v. Now we talk about something about function ua and va for the spherically symmetric matrix. For the spherical symmetric matrix, we can get an approach to how to calculate these functions for this. Calculate the ua and uv. Let f is a spherically symmetric Finsler surface. F equal to length of y, phi, then length of x squared over 2, inner product x, y, x means point, y means vector, and over length of y. Be a spherically symmetric Finsler matrix on the ball. We can express x equal to x1 and x2. X1 equal to rho cosine theta. X2 means equal to rho sine theta. Then partial and partial theta is a Killing vector field of F. So all spherically symmetric Finsler surface admit a non-zero Killing vector field, d theta, partial theta. The approach of the calculator, the UA and the VA, is the three steps. The step one is calculate A equal to ATS. Here T equal to length x squared over 2. S equal to inner product x, y over length of y. The second step is we calculate Fz and Gz for fixed constant x, fixed constant c, where f and g satisfy this equation. Here I is the main scalar, j is Landsberg curvature, and aj means omega j, then partial theta, hat partial theta. The last step is let ua square equals to fza, and va equals to gza over fza. Substituting this equal to 50, 51, and 52, we obtain the normal form for non-spherically symmetric Finsler matrix of constant curvature. For example, we can calculate this one. Think for the function metric on the unit desk D2. This is a function metric. This is a Klein metric, and this one is one form. We can find UA equal to the square root 1 plus 4a squared, and VA equals to minus 3a over 1 plus 4a squared. For this case, we can calculate the UA and the VA in the normal form. So in this lecture, we discuss two parts. The one part is a constant curvature surface with two-dimensional isometric slope. And the second part is discuss the one-dimensional globe. Just means one Killing vector field. We can describe the surface of this Finsler surface. This is one factor, and another one we can reconstruction. Can find many examples. Now we find several examples is singular. Maybe we can find a new example is non-singular, is regular. Okay, that's all. Thank you.
Thank you. Are there any questions or comments? Yes.
In your singular examples, how does the group acts? Yes, there should be a two-parameter isometric group, right? Can we see it? What it does? Well, it has a generator along x2, one Killing field. What is the other Killing field, or what is this?
This is just the first case is we have a two-dimensional isometric globe, and the second case a one-dimensional globe.
Yeah, the first case, the first example, which is singular with that formula.
Oh, you mean the example?
Yeah. You have a two-parameter family of examples of constant curvature,
yes,
and
yes.
two-dimensional isometric group.
Yes.
well, you started from the assumption that there is a group and arrived at example. Is there that group there after all?
Oh, in general case, I think it's difficult to find reconstruction. We just set the S equal to 0 and R equal to is 2 or 3 something. It's
You know what it is? It's the non-abelian group of dimension 2. It's the solvable group. Yeah, that's right. It's I mean, if you turn it at 90 degrees, it's so one of the symmetries is just translation in the x-axis. The other is just scaling.
yes.
Also, I think
Okay, thank you.
I think the key issue in his lecture that he studied singular metric. Yeah.
Sorry.
Even for homogeneous, homogeneous, non-compact, homogeneous space, it can have positive curvature. Yeah, because it's singular, it's not smooth, so we cannot use the Banach-Meyer's theorem or Algebra theorem to argue. Yeah.
Yes.
So it confused me quite a long time.
Yes. Can find a lot of examples. Huh?
So it's not a question. I'd like to make a comment, yeah. And actually, what I would like to do, may I go to the blackboard? I like to link this result with the talk of Yuri Nikolaevsky, yeah. And basically, it's just result and the discussion after it, yeah. So sorry for taking your time, but so the theorem, if you formulate one of two theorem, I mean not the construction, but let us do it as a theorem in short words. This is the following one. If you have two-dimensional surface, its local result, Finsler metric of constant flag curvature with two-dimensional isometry group, and then there are different answers, yeah? So let me just formulate it as following. Is Minkowski.
Minkowski? Okay, two-dimensional.
Yeah? So it's one of the version of the result, yeah? So what I would like to relate to the talk of Yuri by saying that this condition, constant flag curvature, is not necessary here. So it's still Minkowski out of it, and it could be derived from the methods which were used in the talk of Yuri. Because in the case we have two-dimensional isometry group, then this two-dimensional isometry group is also isometry group for Binelli-Legendre metric. Binelli-Legendre metric has two-dimensional isometry group, which means that this is usual group of translation with respect to x and y, x standard translation to the.
What about the hyperbolic language? Because three-dimensional group.
No. Minkowski space would have two-dimensional group only. So Binelli-Legendre has at least two-dimensional. So then, and therefore our Finsler metric should be invariant with respect to translation. It's Minkowski. But the result of Professor Moore is not local, but micro-local. Micro-local, yeah? And then the condition that constant flag curvature was essentially used. And indeed, one can produce non-trivial examples. And the non-trivial examples are due to the fact, which Robert pointed out, that the isometry group is kind of funny. It's the one which cannot exist for Riemannian metric. So its algebra has the property it's generated by two vector fields, V and U, and V with U is U. Yeah? So, and this allows to construct micro-local examples with this two-parametric freedom. Sorry for taking the time.
Okay.
I have a question concerning how can you define that average, the remaining metric when Finsler metric is singular? So I don't know. For smooth, then we know how to average that in some sense. But it's singular. So yeah, maybe something we can discuss after.
Maybe
If I go back to your, first of all, thank you for the talk. It was extremely rich. If we go back to the example with two Killing vector fields, you, in all cases, you always reduce everything to two parameters S and T. Can you say a word about their geometric meaning of this parameter, or it's only something that shows up in the equation? Because they should have a geometric meaning. Maybe it's hard to do. So what can you comment on that?
I hope find to the geometry meaning.
Okay. So it's still some work.
Yes.
Okay.
Continue to work.
Okay.
Okay, thank you.
Okay, thank you. I'm sorry, we have to stop for the questions right now. And thanks again. We're a bit late, but I propose that we resume in 5 minutes, okay?
Okay. We can do it in 10 minutes.
We resume in 10 minutes, okay? Decision of the organizer. Okay, the last speaker this morning is Thomas Mettler from Frankfurt Universität, weil the structures on Finsler two spheres of constant positive curvature.
Well, thank you. And of course, thanks to the organizers for putting together this very nice event, and also for giving me the possibility to talk about my work. It's a pleasure being in Pisa. So I think, similar to many speakers here, I'm not a Finsler geometer. So this is sort of a spin-off story from my work, which is mainly in projective differential geometry. And it actually dates back to my thesis, but it got never published because once I've written it up, I'd learned that Robert Bryant had previously sort of obtained very similar results, some of which Robert actually just mentioned this morning. So this talk, or the last bit of this talk, can be understood as sort of an addendum to what Robert said this morning about Finsler surfaces of constant flat curvature. But I want to take a different angle, start sort of at the other end, and that is in projective geometry. So throughout my talk, M will mostly be a sort of a smooth surface, oriented typically, and I want to look at torsion-free connections on the tangent bundle of that surface. So if I have a torsion-free connection, I can of course talk about the geodesics just as an immersed curve having the property that the velocity vector is parallel along the curve. So this gives me a very simple and natural equivalence relation on the space of connections. So I call two connections projectively equivalent if they have the same geodesics once I forget about parametrizations. Or more precisely, so every geodesic of nabla can be reparametrized to become a geodesic of nabla prime. And so you could ask, and the projective structure is then simply an equivalence class of connections. Okay? So you can ask concretely, what does it mean on a computational level for two connections to be projectively equivalent? And there's a simple relation, which is the following. It's a lemma due to Weil. So two connections are projectively equivalent if and only if their difference, which is a tensor, is pure trace. Or explicitly, if there exists a one form, say theta, so that the difference of the two connections can be written in this particular form. Right? So that's sort of the setup. Now, if you're a Riemannian geometer, there's a very obvious question that comes to mind. So if I give myself a projective structure, is there a Levi-Civita connection in that projective class, right? Can I cook up a Riemannian metric that lives in this projective class? And this right away gives you a partial differential equation. So this is our question. When does a projective structure arise from a Levi-Civita connection? And there's an obvious nonlinear PD you can write down. You say, so this nabla here is some representative connection of my projective class. And so the PD is just that the Levi-Civita connection of my metric minus nabla has to be pure trace. So if you were to write this out in coordinate, it's not a particularly nice system to work with. It's obviously a nonlinear system, and it's certainly not easy to analyze that system. So you have to be somehow more clever to make progress in this question. And so Roger Liouville, which is a younger relative of Joseph Liouville, actually already looked at this in 1889. And what he observed is, so this is formulated for the case of 2 dimensions. So it turns out that the Levi-Civita connection of some Riemannian metric lives in the projective class if the metric multiplied with this weight here is in the kernel of a certain first order linear differential operator. I mean, for what follows, the precise form of this differential operator is not too relevant. So let me just mention that you can rephrase this as a linear PDE system, which is certainly not obvious when you think back to the previous slide, right? It turns out you can generalize this. I mean, the question obviously makes sense in all dimensions, and you can generalize this, this result of Liouville, and this generalization is due to Mikes and Sinyukov. Okay, but once you know that, you would like to know, explicitly what are the obstructions for a projective structure to be, as we say, metrizable. And this is a result, as you can see, quite a bit later, in 2009 by Robert Bryant, Maciek Dunajski, and Mike Eastwood. So they figure out the necessary and sufficient conditions for a 2-dimensional projective structure to locally be metrizable. So it turns out in 2D is sort of the most difficult case because, so this is an overdetermined system, right? So it turns out this is an overdetermined system, and in 2D it's just overdetermined by one equation. The higher up you go in dimensions, the more overdetermined your system becomes. So, and in a way, the easier it is to, to cook up obstructions to solvability. So, but they obtained this result. And along the way, they show the following fact. So in 2D, this is due to Robert, Maciek, and Mike. And sort of the general case was studied by Vladimir and Mike Eastwood. So if you have some projective structure, what you can show is that the metrics having the property that the Levi-Civita connection lies in the projective class, they correspond to certain parallel sections of a certain vector bundle that is equipped with some connection. So given a projective structure, you can cook up a certain vector bundle and the connection so that the solutions to this problem up here just are the parallel sections of that vector bundle that satisfy a non-degeneracy condition that guarantees that you actually have a metric. Okay, so this is a sort of a nice step in this story. So this is a conference about Finsler geometry. So you might immediately ask, so what about Finsler? So is it true if I give you a projective structure, or more generally some path geometry, so a prescription of a path for every direction in each tangent space? Are those paths the geodesics of some Finsler metric? Sort of the obvious variant of that question. And it turns out that's true. So at least locally, although it turns out also globally, as long as you assume that the space of geodesics admits the structure of a smooth surface. Okay. This is obviously a pretty restrictive condition, but locally that's always, you can always assume that to be true. So locally every path geometry, or to be precise, symmetric path geometry is Finsler metrizable. And you can go on to higher dimensions, and there are also results in this directions, some of which by authors that are here. So I met Tom and Sultan yesterday. Yeah, hello. All right, so that is sort of certainly a geometrically very natural question, and that is a sort of natural generalization, or a natural sort of version of that question, and that is sort of obviously motivated by thinking of this as a kind of inverse problem in the calculus of variations, right? So you want to find the length functionals whose geodesics you have prescribed, and first the length functional was constrained to be a Riemannian length functional. Now you go to the Finsler case, right? But there's another direction you can go, and that is looking at Weil connections. So we had our projective structure, and the question was, does it contain a Levi-Civita connection? So is a natural generalization of a Levi-Civita connection? Well, a Levi-Civita connection is a connection that has the property that its parallel transport maps are linear isometries for some metric. But you could say, okay, I just want my parallel transport maps to be conformal maps. And that would be a way to relax this condition. So a while connection is simply a connection that preserves some conformal structure. So in the sense that the parallel transport maps are angle preserving. And so on a computational level, if G is a representative metric, a while connection has a property, so the covariant derivative of the metric isn't necessarily 0, but a multiple of the metric, and the multiple is the form theta. This already connects to Robert's talk. So the theta here is precisely Robert's beta. So these beta geodesics we had before, they're simply reparameterizations of the geodesics of a while connection. In particular, you can, physicists interpret them in terms of magnetic geodesics and so on. So, but now the question is, we just sort of repeat the question in this slightly relaxed setting. So given a projective structure, does it come from a while connection? Right? I could say, you can explicitly write them down. So this is how while connections look like. If you pick some representative metric in the one form, so this is how a while connection looks like. So here, this is the dual vector field to theta with respect to G. Okay? So you can sort of use the differential operator of Liouville to phrase this as a differential equation. So it turns out the 2D projective structure comes from a while connection preserving the conformal structure G here, if there exists a one form such that, well, this equation holds. So if you see this equation for the first time, it's maybe slightly misleading because you could think, well, solve for theta. You could get the impression that it's somehow an algebraic problem. But it isn't, because this is 3 equations really, but theta only gives you 2 degrees of freedom, so you cannot just do this algebraically. So there's an actual PD to be solved. But it turns out you can locally always solve it in 2 dimensions. In 2 dimensions you can always solve it locally, so every 2D projective structure arises from a while connection. Okay, so this is a first observation. Okay, but it turns out, so this PD problem actually nicely connects to complex geometry and holomorphic curves. And this is in a way not really I would say not really the nice way to write this as a PD, because, so first of all, it's a PD for a representative metric. It would be sort of nicer to directly write down a PD for the conformal structure. It would be sort of more pleasant. And so how do we do that? Well, conformal structures in 2D, conformal geometry in 2D is special, obviously, because it's the same as complex one-dimensional geometry. So, or in other words, if I have an oriented surface, a conformal structure is the same as an orientation-inducing complex structure, right? So how do you describe complex structures? Well, if you're willing to sort of fix an initial complex structure, another complex structure is described in terms of the so-called Beltrami differential. So just before we get to that, I hope no one's insulted if I give you a very brief reminder of some complex geometry facts. So take some complex vector bundle over a Riemann surface. So here J is my complex structure, so an endomorphism of the tangent bundle that has the property that it squares to minus the identity. So if I have bundle valued one forms on my surface, I can decompose them into 2 pieces, the 0,1 part and the 1,0 part, where the 0,1 part just consists of the one forms that have the property applying J is the same as multiplying with I, and the 0,1 forms are the ones where applying J is the same as multiplying with minus I. And so every form can be decomposed into a 1,0 part and a 0,1 part. Yeah? In case of the trivial bundle, so you get the usual complex valued forms. So there's actually a typo, so I'm not suggesting here that the the 1-0 forms that are holomorphic, right? So that I should sort of include a set bar here, right? So these are just forms that you get by by multiplying some complex function with dz, where z is a local holomorphic coordinate, and here you multiply with dz bar, right? Okay, so now to the Beltrami differential. So say we fix some complex structure on our surface. Now we want to describe another complex structure. How do we do that? Well, let's pick some representative metric of our, associated conformal structure. And we can, with respect to a local holomorphic coordinate system, we can obviously describe it in this very explicit fashion. And we get a new complex structure J prime, which is just, multiplying by pi half in positive direction with respect to G here. So a complex structure is entirely determined in terms of its 1-0 forms. So how do the 1-0 forms with respect to this new complex structure look like? Well, it is just, elementary computation. You compute, and that's the formula you get. So you can write then in terms of dz. So this is sort of an uninteresting bit, what you have here. The interesting bit is this mu here. Mu tells you how the new complex structure is different from the original one, right? And if you compute, this is how mu looks like. And turns out invariantly, so if you multiply it with dz par times this partial derivative set, then you get something that is independent of your choice of coordinates. And this is the Beltrami differential, right? Fundamental object, in particular in Teichmüller theory. And what you can easily compute is how do the holomorphic maps look like with respect to my new complex structure. So if you go through the computations, you learn that they must satisfy this equation down here, which is the famous Beltrami equation. So try to keep this in mind in case you haven't seen it before. So sort of, right, so if mu were 0, that would mean you get the same complex structure that you originally had, and then your holomorphic functions would just be the ones in the kernel of the del bar operator. Oops, there's the line here a bit too long. So, but in terms of a new complex structure, you have this extra bit. So this is Beltrami's equation. Okay. So, but in our case, so now I just fixed some complex structure and described the new one relative to the given one. But we don't have a given one, right? So that was an artificial choice. So it's a natural question to ask, or phrased differently, the Beltrami differential is a relative object, right? It describes a complex structure relative to a given one. You could say, is there a notion of an absolute Beltrami differential? It doesn't require any initial choices. So if I were to, you could say naively, if I don't have a local holomorphic coordinate on my surface, I can still happily take any coordinate system and write my metric as I did before, write down this mu. So the question is, what have I written down? Now, there's certainly nothing tensorial here, when you look at the formula. So this is not going to be a tensor, but it might still be a section of some natural bundle. What is that bundle, right? And so the goal will be to think of mu as a section of an associated bundle to the oriented frame bundle of my surface. So I have an oriented surface. I look at its oriented frame bundle, which is just the principal right GL+2 fiber bundle whose fiber consists of the oriented basis of some tangent plane, right? So this is a nice fiber bundle. And I want to think somehow as this guy here as being associated to, well, what do I need? So now I need to cook up some fiber bundle. So I need some action of the structure group GL+2 where, well, this thing here, if you compute, has modulus less than 1, right? So this has modulus less than 1. So this takes values in the open disk in the complex plane. So what we need is an action of GL+2 on the disk. Okay, we don't have to be super creative to come up with an example of such an action, right? GL+2 acts by Möbius transformations on the upper half plane. we can identify with the disk, and hence we get a natural GL plus action on the disk, and hence we get a natural associated disk bundle. Okay, I should also say, so F carries the soldering form, right, the tautological form, and so you can show that you can, thought about this properly. This is a section of this disk bundle. Okay, this is a section of this disk bundle. So I want to call that the Beltrami bundle. I'm not sure, maybe, maybe this has been around in the literature before. I mean, I certainly looked for it. I couldn't find an obvious reference. I mean, happy to use another name, but okay, let's call it the Beltrami bundle. So what you can show is this disk bundle that you just cooked up is isomorphic to the frame bundle by CO2. So this is the linear conformal group, by which I just mean rotations times scaling. Okay, so it's not very surprising that this is all isomorphic because, one of these absolute Beltrami differentials, it's just supposed to describe a conformal structure, right? Just supposed to describe a conformal structure. But what is a section of this thing here? Well, it's a basis at each tangent space up to rotation and scale, which is precisely what a conformal structure gives you, right? And, this is a GL plus 2 bundle, so if you divide GL plus 2 by this linear conformal group, it's like SL2 mod SO2, which is the disk. So this, this works out. So how does this all relate to, what I did previously? So now we have a projective structure given, and we want to figure out, is there a Weil connection in the projective structure? So in particular, if I take some representative connection of that projective structure, I can define what I want to call formal del and del bar operators. So why do I call these things formal del and del bar operators? So what are these vector fields here? So we have a connection, so we have a horizontal space, and in particular we get two vector fields that have the property that evaluated on the tautological form, we get delta ij. Okay, so these are distinguished vector fields. So what's the relation between del and del bar? Say you had a Riemannian metric, you could reduce to the orthonormal frame bundle, which happens to be the unit tangent bundle if you fix an orientation. You could reduce to the orthonormal frame bundle, and on the orthonormal frame bundle you still have the tautological form and the Levi-Civita connection form. So these vector fields are well defined in the case where you have some fixed metric. If you actually go through the computations, del and del bar sort of really correspond to this thing here. Okay, it's a little computation. So here's sort of the punchline. So we have an absolute Beltrami differential, which we can think of as being a conformal structure. So this is supposed to be some function on my frame bundle, which is equivariant with respect to this Möbius action. I can cook up a 2 form. So this is my 2 form here. Turns out this is the pullback of a 2 form on my surface. And so this is actually, this last bit is based on a joint paper with Gabriel Patenine. So this 2 form vanishes identically if and only if this is projectly equivalent to a Weil connection with respect to the conformal structure defined by mu or G here. Okay. So this is actually, if you look at this 2 form a little bit more carefully. So here we have mu prime prime, which is sort of del bar, minus mu del mu, okay, on a formal level, which is precisely Beltrami's equation in the case where f is mu. Okay. So sort of on a formal level, this looks a little bit like Beltrami's equation here. So you could sort of think, well, this mu is somehow supposed to be something holomorphic, right? So this is sort of a naive thought you could maybe have. And it turns out that can be made precise. So this is a result which has its origins in twistor theory. By the way, how am I doing with time? Okay, not too bad. So this is a result that has its origins in twistor theory. So if you have some connection, turns out it defines a complex structure on the total space of this bundle B, and which actually only depends on the projective equivalence class of the connection. So this bundle B is a complex surface. It's a complex surface fibering over our surface that is equipped with a projective structure, and its sections are precisely the conformal structures on the surface M. Okay? And the observation is a section here, which is nothing than a conformal structure, is a holomorphic curve. So in the sense the image of my section is a complex, admits the structure of a complex one-dimensional submanifold, if and only if this two-form vanishes, or in other words, if my connection is projectively equivalent to a Weil connection. Okay? So in a way, mu is a holomorphic object. Okay? So this is all a bit abstract nonsense currently. So, but I think it would be interesting to know, if there's something deeper going on here. Okay, so finding a compatible Weil connection in a projective class is finding a holomorphic curve into this complex surface. Right? So that's the upshot of what we've learned so far. So how does that connect to Finsler geometry? Right? So you can ask, well, how does that surface look like for concrete cases? The most obvious case to look at is just take the two-sphere and the standard projective structure whose geodesics are just the great circles. So in that case, you can prove that B is simply CP2. That is not too surprising, CP2 with an RP2 removed. So you can sort of see that in part. So let's take some point on the sphere. Let's take some point on the sphere, so which we sort of think as sitting inside R3. If you look at the tangent space to that point, you can think of it as the orthogonal complement of X with respect to the standard metric in R3. Right? So a point in my bundle B is just a basis up to rotation and scale. So it gives me two vectors. So here is my basis, but now up to rotation and scale. Right, up to rotation and scale. So this is a vector in C3 up to multiplication with a non-zero complex number. So this is an element in CP2. Right? So we have to cut out RP2, because RP2 would correspond, these two guys being linearly dependent. So you remove the RP2 bit. Okay, what I just said obviously doesn't tell you that the complex structure is the standard complex structure. Okay, that's the tricky bit of this lemma. There's actually something to be proved there. But once you know that, you can classify the Weil connections on the two spheres whose geodesics are the great circles. So these are just the holomorphic curves, the holomorphic, rational curves in CP2 with an RP2 removed. Okay? So the Weil connections on S2 whose geodesics are the great circles, they correspond with the smooth quadrics without real points. So if you're familiar with Robert Bryant's amazing paper on projectively flat Finsler structures on the two-sphere of constant curvature, then you might say, well, I've seen these quadrics before, right? So these smooth quadrics in CP2, they also show up in Robert's work in Finsler structures on the two-sphere with constant Finsler-Gauss curvature and linear geodesics. That's an obvious question. Why is that the case, right? And so this is the result I mentioned, which has some overlap with what Robert said this morning. So if you have a sole projective structure, that just simply means a projective structure, all of whose geodesics are embedded circles. So if you have a sole projective structure on the two-sphere that comes from a Weil connection, and that Weil connection has the property that its Ricci curvature, or the symmetric part, right? In general, a connection need not have symmetric Ricci curvature, general connection. So the symmetric part of the Ricci curvature is positive definite. Then you get a Finsler structure of constant curvature and with periodic geodesic flow. And you can go back. Okay? So this is the reason why somehow these smooth quadrics make an appearance both in Finsler geometry and in projective geometry. And so let me just roughly sketch maybe one direction. So how you go from one to the other. So suppose we have our Weil connection on this two-sphere, which is sole and has the property that the symmetric bit of the Ricci curvature is positive definite, which is just this quantity here. Right? So here obviously being the Gauss curvature with respect to G, and here co-differential. So this thing here has to be positive definite. So you look at the unit tangent bundle of that metric. It has a natural co-framing consisting of these three forms, alpha, beta, and the Levi-Civita connection forms. So I've written them down here. So J is here rotation by pi half with respect to the metric. And psi, the Levi-Civita connection form. Then you cook up a co-framing as follows. So here we have the hot star of theta minus psi. Here we have a multiple of beta and a multiple of alpha. And what's the geometric significance of that co-framing is, so the first two forms, they're, if you remember Robert's talk, they're sort of, in particular this form must have been on the slide somewhere, I think. So these two forms, if you look at the foliation defined by these two forms, the leaves of that foliation, they project down to be the geodesics of your Weil connection. Well, these are the two defining forms for what Robert called the beta geodesics. Okay? And so why do we normalize in this particular fashion? Well, we just normalize so that these three forms, they satisfy the structure equations of a generalized Finsler structure, or just to be brief, a Finsler structure of constant Finsler Gauss curvature. So this, you want to think of that as the canonical co-framing of Cartan on the integratrix bundle, right? These three forms. So these are the structure equations written down explicitly. And yeah. So I already said that. So the leaf space of this foliation is, yes. So the leaf space is the space of oriented geodesics of your Weil connections. And so there's a result by Lebrun and Mason that enters here. So they show in general, if you have a sole projective structure on a compact surface, then the space of oriented geodesics is S2. So here it means you get a smooth surjective submersion onto S2, whose fibers are precisely the leaf of this foliation. And you can then use the dual framing to these one forms here, so this is the dual framing, to define a map from the unit tangent bundle into the tangent bundle of the two-sphere, and you get to prove that the image is precisely the indicatrix bundle of the resulting Finsler metric. Okay, so that's how you that's how you go from one direction to the other, to the Finsler world, and the other direction is a little bit similar. So I think my time's up anyway, so I'll stop here. Thank you for your attention.
Any questions or comments? No? Maybe I have a question, a naive question, about this projective structure meeting Levi-Civita connection in the class. Is there any global result? I mean,
not in general.
Closed surfaces or things like that?
I mean, not in general. I mean, there's some characterization for sole projective structure, which is global due to Lebrun and Mason. Right, so you stick to the sole projective case. And then LeBron and Mason, they have a characterization of the ones that come from a Levi-Civita connection. But as far as I know, I'm not aware of a general global characterization.
There is another set of such metrics which are projectively flat, for instance. These are the Hilbert metrics on a convex set.
Yeah.
RP2.
Yeah, I mean...
There are global extensions. They exist if and only if the boundary has some properties. This convex set is divisible.
Yes.
So
yeah,
you
exactly.
can read on the representation of the fundamental group into SL3 R. They are no. They are not smooth. Exactly. That was my question. Because Lebrun Mason, in what I remind, used some C4 or regularity or something like that.
Yeah, I mean, they're not smooth, and in a way, these are sort of this properly convex world is sort of disjoined from this Weil world. So in a sense, so I mentioned that locally every projective structure in 2D comes from a Weil connection, but obviously not necessarily globally, right? And so there's a natural question, find an example of a projective structure that, locally it always comes from a Weil connection, but globally it doesn't. And this is actually a recent joint work with Gabriel Paternine, where we show precisely that these properly convex projective structures, they do not come from a Weil connection globally, unless you're hyperbolic.
Yeah.
So they're sort of the other end, in a way.
Smooth.
Smooth.
Yeah.
Then it is smooth.
But if it's smooth, then it's sort of, you need smoothness, and his example essentially not smooth. They only see one.
Well, now we're sort of confusing things. So this is a regularity of the Finsler metric. Now I'm sort of talking about, these properly convex projective structures. They still come from a smooth connection.
Yes, Hilbert geometry gives very smooth projective structures on surfaces.
Yeah.
Except the Hilbert metric
the Hilbert
is not
smooth.
Yes,
that's the point. Yes.
Is not smooth. Yeah. Good. Thank you. Any other questions or comments? No?
Okay, welcome to this first parallel session on Finsler geometry and general relativity. And the first talk is by Ettore Minguzzi from University of Florence, and he will talk about relativity theory and modified indicatrices.
Thank you very much. Thank you. I'm so happy that there is a session on Finsler gravity, even close to my home because I live nearby. And also that my talk is the first one of the session because it will be of foundational character, especially on the kinematics of these Lorentz-Finsler theories. So, as you know, Einstein general relativity is based on a differentiable manifold with the Lorentzian metric, and the dynamics is determined by the Einstein equation, where R mu nu is the Ricci tensor and T is the stress energy tensor. Let us have a closer look at the kinematics of general relativity. At each point we have a quadratic form which has this expression where y mu are coordinates induced on the tangent bundle from a local coordinate system on the manifold. So here we recognize the set of time-lag vectors, which are those that have, so to say, negative square and are future-oriented, and the boundary, which is the set of like-lag vector. Then we also recognize that there is a special hypersurface inside the cone of time-lag vector, which is the hyperboloid, which physically is the space of observers, and in Finsler geometry is the non-compact indicatrix in this Finslerian case, as we shall see. Still in general relativity, so we have a distribution of cones over the manifold and the distribution of hyperboloids inside the cones. And the curve is time-like if the square of the tangent vector is negative, or let-like if it's 0. So the distinction is from massive and massless particle. Then the proper time is the integral of this function here that will play the role of Finsler function in the general theory. So in an anisotropic generalization, we first observe that in general relativity we assume the cones to be round, which means that the intersection with respect to an hyperplane gives you an ellipsoid. And so the idea is to replace round cones with convex cones, which possibly are just small perturbation of the round cones. So the shape of the cones is going to be a new dynamical object. This means that the speed of light could be slightly, in some cases, anisotropic. So we start with a smooth manifold with the same induced coordinate on the tangent bundle. And we would like to recover the metric this time from a Finsler Lagrangian. This is the setting of Lorentz-Finsler geometry. Is basically that this Lagrangian is defined over a subset of the slit tangent bundle. I call Finsler Lagrangian L what is usually F squared in another more usual notation. So this is the metric, and we ask that it is Lorentzian in this set D. This, of course, from positive homogeneity we have these qualities. In the usual Riemannian case, G, the metric is independent of Y, and so the Lagrangian is quadratic. But as we said, L can be situated just in some model on a subbundle of the slit tangent bundle. Physically, this is not a problem as far as this subset here contains what can be recognized as the set of observer, the set of time-like vectors, which we identify with the locus where this function L is negative. There is also another convention. This choice here is related to the choice of signature, which is not probably the best one in the Lorentz-Finsler case. The other one is more leads to simpler formulas with less minus signs, but this is the most accepted in mathematical relativity signature. So what about this domain? There are two approaches. You can demand Lorentzianity just inside the convex sharp open cone, omega, which is your domain D, which you interpret as the cone of time-like vectors. So L is negative there. It goes to 0 to the boundary, and L is this quantity here, where F is the usual Finsler fundamental function. This is the approach by Asanov, who worked inside a cone, basically. In beam approach, instead, you demand Lorentzianity over the whole tangent space minus the origin. Okay? And then there are mixed approach, let's say, or improved approach with respect to Asanov, in which you take this scheme here, but you add additional regularity condition at the boundary, that is in the set of like vectors.
So your Lorentzianity condition means that d omega, the indicatrix, is concave, or strictly concave, or what?
Yes, in the end, it implies indeed that it's strongly strongly concave. Okay.
It's equivalent.
It's yes, under if it is C2, a strongly concave, it's equivalent. You need the regularity of the indicatrix. So the problem is that with the first approach, it's difficult to define like geodesics. Well, because you need this regularity at the boundary, because like vectors lives here, and also you have to add the cone as a data, let's say. In beam approach, there is this problem. If you look at the set of time-like vectors, the problem is, are these sets convex cones? And more importantly, or as important, are they two in numbers so that we can identify a future cone and the past cone? So beam proved that in the space-time dimension 2, there could be more than two components. here are some reversible examples. First, he gave this example in space-time dimension 2. This has 4 cones. So future and past, and this is a problem. And then he gave this example in 73 that the same happens in higher dimension, where alpha is a sufficiently large constant. It has 4 components. This was a serious problem for the rigorous interpretation of Lorentz-Finsler theory, right? But fortunately, I was not aware of these counterexamples because I proved that, in fact, in space-time dimension larger than 3, if your Finsler Lagrangian is C2 as Lorentzian Hessian everywhere, then and it's reversible, then the components are precisely 2. And they are convex sharp open cones whose closure do not intersect. And the Legendre map to the momentum space is a bijection. So it turned out, in fact, that the counterexample is incorrect. The determinant was 0 at some points, but it was very difficult for him at the time to find this problem. I found it with Matematica that there was, in fact. So spacetimes in the Lorentz-Finsler, in the beam sense, are physically meaningful. It's acceptable as Asanov. Now you can ask, okay, let me consider the conic approach by Asanov at the regularity at the boundary. What happens? Well, it happens that you go back to the beam theory. So take a Lagrangian which is over an open sharp. Sharp means pointed, no affine line inside the cone, which is C2 inside, C0 up to the boundary, negative inside 0 at the boundary, positive homogeneous degree 2 with the Lorentzian Hessian. This is Asanov picture. But suppose that L is also C2 extendable, so that its Hessian, G, is Lorentzian, also at the boundary, and in such a way that the differential of L is non-trivial at the boundary. Then this Finsler Lagrangian is really the restriction of a Lagrangian defined all over the slit tangent bundle and Lorentzian all over the tangent bundle. The point is that I could not prove that the Lagrangian can be chosen reversible, okay, but this is not a big problem from the point of view of the interpretation. So both approaches are acceptable in a set. Now, if you define, as usual, this function f in this form, in the Finsler case, then f is concave and positive homogeneous on the future causal cone. And on this future causal cone, we have generalization on the Finsler of the so-called reverse triangle inequality or Lorentzian geometry, which states this fact. You pick 2 causal vectors, you add them, you get another causal vector, and there is this relationship with equality if and only if they are proportional. Same for the reverse Cauchy-Schwarz inequality. You pick 2 vectors, their scalar product, and here you can place any of the 2 of your choice. It's always greater than the product of the fundamental function over the vectors. These are important because also they survive under very weak regularity condition on the function f. In fact, many results of causality theory pass through to the Lorentz-Finsler case. I'm not going to enter into the details of causality theory, which is the theory by Hawking and Penrose to deal with singularities, but that pass through. Just these slides. Most causality results do not really read regularity in the vertical variable y, and just upper semi-continuity on x, if you follow this approach. First, you define a proper cone structure as a distribution of non-empty convex sharp cones, such that if you consider the cone bundle formed by them, then this is a closed subbundle, which is proper in the sense that the interior of the bundle intersected with the fiber of every point is something different from 0. This is kind of structure that also Stefan Sur also worked on that. But then we add another ingredient. We introduce this function f, which is the Finsler fundamental function, positive homogeneous concave, which vanishes at the boundary. And we consider this product manifold times R and define on this product this cone structure. We use f to build a cone on the product. This gives a cone distribution on the product. If this cone distribution is a proper cone structure in this sense, then we call MF a proper Lorentz-Finsler space, also called a space-time. This closed condition is an upper semi-continuity condition on F. So the cone distribution and F are upper semi-continuous, not even continuous. And you get many results. Is an example, the generalization of the David-Seffer theorem. If the space-time is globally hyperbolic, then any two causally related events are really connected by a causal curve that maximizes the proper time, the Lorentz-Finsler length. But I don't enter into the definition of global hyperbolicity. In fact, from now on, I study just geometry at a single point, on a single tangent space. So I recall this simple algebraic lemma: any two bilinear forms are proportional if Lorentzian bilinear forms are proportional if and only if they share the same time-like cone. Since the volume form induced by the metric, that by the bilinear form, scales in a different way, if you impose the identity of both the induced cone and the volume form, you get the same Lorentzian bilinear form. So as a consequence, two space-time metric coincide if and only if they induce the same distribution of time-like cones and the same volume form on space-time. So we would like to preserve this property at the Lorentz-Finserian level. That is, we want space-time to be the sum of two ingredients, the space-time measure and the conic distribution. But now here there is a problem because we have a cone which is not isotropic. And from there we would like to select an hypersurface inside it, which has to play the role of observer space. And we have so many choices in Finsler geometry. You can choose many hypersurfaces, while we want one. So idea, we use a affine differential geometry. On an affine space, for us is the tangent space at a point. Any hypersurface can be assigned a natural transverse field, which is called the affine or Blaschke normal. It's constructed like this: you pick a point at the boundary, you consider the tangent space at the boundary, you move up the tangent space, you find the sector, you find the barycenter of the sector, you move back the plane where it was in the beginning, the center of mass moves, and the tangent to the curve is the transverse. Here we did not use a scalar product to find the transverse, just a volume form, but in fact not even a volume form. So here are some detail more in detail what is going on. You take the affine space with this volume form, you take the immersion F of this manifold N and codimension 1. You take a distribution of transverse vectors. So you can now split any object, for instance vectors tangents to your affine space, into elements tangent to the hypersurface plus elements proportional to the transverse vector. And since you have a derivative in the affine structure of the affine space, you get this Gauss formula, and Weingarten formula give you an affine connection, a bilinear form which is symmetric, which is called the affine metric, shape operator, and one form. So the Blaschke normal is selected by this condition. There is just one transverse choice of transverses, which is equiaffine. And there is a compatibility condition. The volume form that you get using this affine metric is the same as that induced on the surface, on the upper surface, by the volume form of the affine space using the transverse. If we introduce, using those ingredients, this object, which is the peak cubic form, we notice we use the affine metric, connection, one form. Actually, the second condition can be replaced, and the transverse field is Blaschke if the second condition is replaced by the traceless of this cubic condition over this cubic form. Now, if the lines that selected by this transverse intersect at a point, then the hypersurface is said to be a proper affine sphere. If they are parallel, is an improper affine sphere, center at infinity. The shape operator, which appeared here, is actually in this case proportional to the identity, and the proportionality constant is called affine mean curvature. The affine sphere is elliptic, parabolic, or hyperbolic depending on the sign of each, positive, 0, or negative. So this is the situation. In general, Blaschke transverse do not pass through a point. If they do, you have an affine sphere. Now, the only compact affine spheres are ellipsoids. This is and the only improper center at infinity affine spheres are paraboloids. What about non-compact affine spheres? Well, Calabi conjectured that every proper non-compact affine sphere is asymptotic to a sharp convex cone, and every such a cone contains a unique affine sphere up to homotheties, asymptotic to it. So this is the cone that we want. We say, for us, the observed space is the affine sphere. Calabi conjecture was proved by Cheng and Yao, parameterized the hypersurface using Klein types coordinate like this, called this variable v, that will make sense as you shall see. And with this function 1 over u, you can parameterize any point on your hypersurface. Then this is an affine sphere. If this function is convex, vanishes at the boundary of this convex set D. The convex set D in this picture is the intersection of a plane cutting the cone. Well, so for instance, for the usual hyperboloid, u is this function, and it vanishes when v has modulus equal to 1. In fact, in our theory, v will be the velocity of the particle as seen from the observer, and d will be the domain of allowed velocity as seen from the observer. In fact, it is bounded. It is round if you are in the Lorentzian theory. Function u will be, in fact, just the classical Lagrangian of the theory. So for us, an affine sphere spacetime is any of the following: a distribution of convex sharp cones plus a volume form, or a distribution of hyperbolic affine spheres with center in the zero section. These two things are the same, because if we fix a volume form on M, you get on each tangent space a translation and invariant volume form. And then from the cone and the translation invariant volume form, you get the affine spheres with affine mean curvature minus 1. Conversely, if you have an affine sphere, there is just one volume form for which the distribution of affine sphere has affine mean curvature equal to minus 1. So you get also distribution of cone because they are asymptotic to the cones. So in this theory, the indicatrix is recovered from the cone. So light tell particles how to move, because the indicatrix tell massive particles how to move. And this here the indicatrix passes from the cone. If you take the dual of the convex cone, or better the polar, inside the polar there is the dual indicatrix, and is itself an affine sphere which you can represent as a Cartesian graph through a function that turns out to be the dispersion relation of the theory. This is the minus the energy. This is the usual E squared minus P squared equal a constant for mass equal 1. It turns out that affine sphere space-time are a special type of non-infinite spaces. We should see that. And we have preserved this correspondence: space-time equal conic order plus space-time measure, provided for us space-time is an affine sphere space-time. We want to preserve this property because we think it could survive at the quantum level. Okay, because at the quantum level we want to preserve order, a notion of causal order, and the notion of space-time measure. So we believe these are fundamental concepts. This is a numerical example. I take the usual hyperboloid. I perturb the cone, making it of this shape, And this is the perturbed affine sphere, which is no more than a hyperboloid. Okay. Now, when I have given any indicatrix, you can get your Finsler Lagrangian. How? Well, you pick a point y, you find that constant s, such that y over s brings you to the indicatrix, and you define f equal to s. In this way, L, which is f squared minus f squared over 2, has Lorentzian Hessian. And this is the Finsler metric. So we can treat it as a Lorentz-Finsler. In a Lorentz-Finsler case, so we ask, what is the affine sphere condition from the Finsler point of view? This is the condition that the mean Cartan torsion vanishes, where the Cartan torsion is the derivative with respect to the vector variable of the metric. Now, it is known that in positive signature, Dike theorem tells you that under this condition, mean Cartan torsion is equal to 0, that your space is Riemannian. Many researchers did not pay much attention to the signature in Finsler gravity and discarded this condition, believed that this was trivial. But in fact, if you impose mean Cartan torsion equal to 0, you don't get a Lorentzian manifold, you get an affine sphere spacetime. Now notice that when you impose this condition, the determinant of G becomes independent of the vertical variable, and so you have a volume form on the base. In Lorentz-Finsler theory, the definition of volume form, for instance, the Busemann or Holmes-Thompson, do not work because they require integration over the indicatrix. But this gives you a volume on the base that gives you a translation invariant form at each point, and with respect to that translation invariant form at each point, the affine mean curvature of the indicatrix, which is an affine sphere, is normalized. So this is the theorem, more or less, that is telling you this. It's not a big deal. It tells you that G can be polarly decomposed into your fundamental function, and this H, which is the affine metric of the indicatrix, basically. And the peak cubic form of affine differential geometry is the pullback of the Cartan torsion. So since we know that if this is traced, it's an affine sphere, the affine sphere condition is the mean Cartan torsion is 0. That is the idea. And then you have, as I said, this volume form on the well-defined of the tangent bundle, and with respect to this volume form, the indicatrix as mean Cartan as mean affine curvature minus 1. And the Monge-Ampère equation is this one. Now, what about lateral geodesics? Lateral geodesics of this equation, you need a C2 condition at the boundary here. Well, this could be a problem because if you calculate the function L for an affine sphere, this could be non-C2 at the boundary. In general, it is not C2 at the boundary. It is C1, not C2. But this is not, seems a bad problem, but in fact it is not so. In fact, it turns out that lateral geodesics do not depend on L. You can get them just from the distribution of cones, or of the light-like hypersurface on the tangent space. If that is regular, it doesn't matter that the Finsler function is not regular at the boundary. You get a flow of lateral geodesics that, however, are not parametrized. That is, the affine parameter does not make sense. But this is a good feature, which so far nobody really noticed. That is the fact that the affine parameter in general relativity for lateral geodesics is a problem. You don't want an affine parameter over a geodesics because light does not bring a clock. It has no physical meaning at all. Lorentz-Finsler geometry is better because there is no such affine parameter. It cannot be defined. If the Lagrangian is not C2. If it is C2, then you have also the affine parameter. But you still have the transport of momenta of the lateral geodesic. So here is an example of a affine sphere spacetime that in a certain velocity limit gives back Schwarzschild, but it does not really solve At least I don't know if it solves some vacuum equations of Finsler gravity. So in general, Finslerian gravitational equations are quite complicated. Now I have this slide because I want to explain the non-relativistic theory, because the nice fact is that the non-relativistic theory is also an affine sphere theory. That is, we talked about affine sphere on the tangent space in the relativistic case, but in the dual, the cotangent space, you have also the dual affine sphere. Now, if you consider a distribution of improper, that is affine sphere, that is paraboloids on the cotangent space, this distribution, notice that the paraboloid has an orientation that gives you a vector psi. This vector psi is a one form which has a kernel, and this kernel is the simultaneity slice in non-relativistic theory. Not only that, the paraboloid, to define it, you need a quadratic form. This gives you, on the other side, a space metric. That is, the distribution of improper affine sphere of the cotangent bundle gives exactly the ingredients of Newton-Cantor theory, of the geometric non-relativistic theory of classical mechanics, let's say. So, in conclusion, in a sense, we have algebraically deconstructed the notion of space-time with the notion of affine sphere, because you don't see any group inside it, right? We have preserved this correspondence. Space-time is volume plus order, which we care of it. And the kinematics is quite developed, at least for these space-times. Dynamics is yet to find a final shape, and the next talk will be, I think, mostly about it. Okay, that's all.
Thank you very much for the beautiful talk. Are there questions?
Do you have any results on the completeness, incompleteness, and the boundary, and what sort of singularities develop?
I have results on singularities.
Yeah.
That is, all the singularity theorems of Lorentzian general relativity pass through to the Lorentz-Finsler theory. Hawking and Penrose, Hawking.
The B boundary and so on.
About the boundary, yeah. I don't know, but I guess it could be done because not so many people is working now. I mean, there is the conformal boundary, which is the most popular.
Yeah. Yeah.
What I tried to check were the singularity theorems, and they ought.
Now, I would like to ask if I have understood well. In the definite positive case, your example, the affine sphere geometry is the Riemannian one. Is
yes,
right?
This is a theorem, yes.
Oh, okay.
In a certain sense, the analog of Riemannian spaces, the Finsler analog of the Lorentzian analog of Riemannian spaces are not Lorentz-Finsler spaces, but affine sphere spacetimes. From this point of view.
Okay.
In a certain sense, the Lorentzian analog of Riemannian spaces are not, one can say, the Lorentz-Finsler spaces, but the affine sphere spacetimes. If you see the Riemannian spaces as the Finsler spaces that you get when you take the mean Cartan torsion equal to 0. Let us define a Riemannian space as that space for which the mean Cartan torsion is 0. Okay, let's see what it is in the Lorentzian signature. This is not a Lorentz-Finsler space. It's an affine sphere spacetime. It's a subclass. So there is more, in Lorentz-Finsler spaces, there is much more freedom. because the indicator is disentangled from the cone, while there is no cone in the Riemannian case. So here we have two objects in a certain sense.
So maybe it's not a question, it's more a comment. I don't know if you're aware that in the 40s, actually already Boozman wrote a long paper about sort of Finsler space-time. I don't remember the name. And
There were the time-like spaces.
Time-like spaces, I don't know if you have time-like spaces.
Yes, he was concerned with geodesics.
And so this research has been reinvestigated recently by Athanas Papadopoulos and Sumio Yamada. They have a very recent paper on arXiv. So in particular, they investigate, for instance, the equivalent of the Funk metric, where you would take the exterior of a convex region, so it's concave from you, and you repeat the construction of the Funk metric or the Hilbert metric if you have. For that, you would need to convex region and provide example, and that there would be the projectively flat example, and it's a different direction. But I mean, maybe
maybe it's connected. Yes, I will have a look.
So I would suggest you take Papadopoulos or Sumio Yamada and go on arXiv, and it's a recent paper.
Thank you. Yes.
Yeah, I think.
Yeah, because this is convex geometry, really. Yes, it's related to many results on convexity.
Yes, also in their paper, but I don't think they look at these affine spheres. So I'm not worried that you're doing the same thing, but it could be interesting for you to look at complementary ideas. So it was a comment.
I have a question to your example. So that looked quite involved, the example you showed there. So,
but this one?
Yeah, for example, is there an easier example, just a general? I mean, this is not a spherical symmetric example, but for the general form, like you have these Bogoslovsky type Finsler functions and so on. Is there some easy example to see what kind of classes fall in the affine sphere spacetimes? And yeah.
So this is a space-time constructed through the so-called Calabi product of affine spheres. That is, there is an operation. You can take products of affine sphere and get new affine spheres from old, and it's the basic operation through which you construct non-trivial affine spheres from known ones, because it's quite hard to solve the affine sphere equation. Well, so you can see here that in fact it's something with an exponent times something with another exponent. They have usually this product structure, this affine sphere.
Is something included, for example, like the Bogoslovsky length measure?
Yeah, so the Bogoslovsky, it's a model which is not an affine sphere. It's no. It's homogeneous, but it's not an affine sphere. Okay.
Is it a deformation of Schwarz?
This is in practice. If these are basically velocity variable in some directions. If these are much larger than this dt, say you can take this equal to 1 or bring it outside, and you take the first order of the quadratic expansion, you get the Schwarzschild metric. So let's say for objects which are slow, this metric will not be distinguished from the Schwarzschild. This is the idea. But this metric has not been built to solve some dynamical equation. Has been precisely built to be an affine sphere and to have as limit Schwarzschild, with the idea that if some equation exists, then it is likely that this solves the equation. This is somewhat it's not the solution, because we are not we don't know for sure what the equation are. At least we are still discussing this point.
Okay.
I don't know if this is. Yes, up to the boundary. The boundary, no. The boundary is inside the boundary, yes.
Okay, I'll say we postpone other questions to private conversation, and we'll meet 5 minutes later, so 5 minutes to 3, yeah? And thanks, Ettore, again. Now, let's continue with Christian Pfeiffer, who will talk from the University of Tartu, who will speak on something very general, Finsler spacetimes.
Yeah, thank you for the nice introduction, and I also like to thank the organizers for this very, very nice conference and giving me the opportunity to present a physicist's point of view on Finsler geometry and someone who's working from the physics side on general relativity and what we think Finsler spacetimes have to satisfy or how they should be constructed to include some physical examples. Because I think the definition for Finsler spacetimes and the construction we just heard is very nice, but we have examples in physics which do not fall in this class, I think, and we want to describe some geometries which are more general. And I want to cook up a definition of Finsler spacetimes, which is, I think, more general and covers more examples which we are interested in physics. And I think the conic Finsler spacetimes, or the affine spheres Finsler spacetimes Ettore just presented to us, are a subclass. I'm not 100% sure of what I will present, but I think they're a subclass. And here just a short comment on my notation. So I will use on the tangent bundle coordinates x, y, where such a tuple represents a vector with components y in the tangent space of M at x. We will encounter functions on the tangent bundle and tensors on the tangent bundle, so tensor components on the tangent bundle. And if you see such an object, that is a tensor on space-time where we insert m times, if it's a 0m tensor, such a tangent vector. Okay, let me start. How does Finsler geometry enter in relativistic physics? And I think it's 2 points where we naturally arrive at Finsler geometry, so non-metric Finsler geometry in physics. That is, when one considers the clock postulate on which relativity is built, and when one considers the space-time description of dispersion relations. What do I mean with that? The clock postulate states that the time an observer measures between two events is basically the length of its world line between the two events. And the most general realization you can think of is a manifold equipped with a Finsler function, because the existence of a Finsler function guarantees a geometric length of a curve. So this we need for an observer's measurement of time. So why not study the most general realization of this? Then the second part is that a dispersion relation is a constraint on the momentum and the positions of the particles, and it can be formulated in terms of a Hamilton function on the cotangent bundle of space-time, and then the motion of the particle is derived by the Hamilton equations of motion. And the dual description of such a system can be done in terms of Finsler Lagrangians. So examples where such systems appear in physics are the geometric optic limits of predictable and quantizable field theories, among which are so-called pre-metric and area-metric electrodynamics, and what is called the standard model extension, where people study non-local Lorentz invariance field theories. Another source of such dispersion relations are Planck scale modified dispersion relations, which are considered to model effects we expect coming from the quantum nature of gravity. So when particles propagate through space-time and they reach a certain energy scale, then they should feel that gravity has a quantum nature as all other fundamental forces in physics, and this may be modeled by a modified dispersion relation. And I want to discuss what kind of properties such a Finsler function or a Finsler Lagrangian must have to be physically viable from my point of view. And to do that, let me recall the role of the geometry of space-time in physics. It is threefold. Namely, that the geometry of space-time encodes causality. That was also discussed in the previous talk already. So from a point we call now the causal structure tells us which events in the future can be influenced and which events in the past influenced the events at this point. Moreover, the geometry of space-time models observers and their measurements, and gravity and its dynamics. In general relativity, this threefold role of the geometry is encoded into a Lorentzian space-time metric, whose light cones give us a causal structure. Time-like curves of the metric and frames of the metric along these curves define observers and their measurements, and the Einstein equations, gravity and its dynamics. So now, the idea is to realize the threefold role of the geometry of space-time in physics with Finsler geometry. The motivation from physics is to address issues in general relativity, like dark matter and dark energy phenomenology, from a geometric point of view. And from the mathematics point of view, I think it's interesting to find a suitable formulation of indefinite Finsler geometry which meets these requirements. And I would be really happy to discuss this with you. Maybe we can improve all the definitions of Finsler spacetimes there are. And the prime example I always have in mind when I talk about this is the geometry of a birefringent crystal, the bimetric Finsler spacetime, which appears when one studies how electrodynamics effectively works inside a crystal. This can be described by a Finsler Lagrangian, which is the product of two Lorentzian metrics, and then the structure in the tangent spaces is given by two light cones, where we have one slower speed of light and one faster speed of light. And the inside, so the time-like vectors with respect to the metric which defines the slow speed of light, are so-called future-pointing stable observer directions. But these are not the only directions along which massive particles can move. Also, massive particles can move along directions inside the time-like cone of the metric which defines the fast speed of light, only that particles moving along these directions, they are unstable. They can undergo a so-called Cherenkov process. They can emit slow light, then lose some of their velocity and, so to say, change the propagation from an unstable direction to a stable observer direction. These are simply effects which appear in physics when you have a medium. And we want to have a definition of Finsler spacetime which includes such examples. So this is a short outline of my talk. I will give you a definition of Finsler spacetimes which guarantees the existence of a causal structure. Then I will discuss how we can model observers and their measurements, in particular the measurement of time, space, and length. And then I will give you an idea how we get dynamical equations which generalize the Einstein equations before I come to conclusion and outlook. Okay, notation I just said. Maybe the only thing I missed is that I denote the coordinate basis of the tangent and cotangent spaces of the tangent bundle by partial A, and these bar partials here are the derivatives with respect to the directions. Yes, so this is my definition of Finsler spacetimes, and I will read it to you, and then we'll go through it step by step, and I tell you why I think all these points are necessary. So, a Finsler spacetime is a smooth manifold equipped with a smooth real function, which we call the Finsler Lagrangian, which is on the slit tangent bundle, and it shall be R homogeneous with respect to the direction. It shall possess a so-called L metric, which is a second derivative of this function with respect to the directions, which shall be non-degenerate not everywhere, but nearly everywhere. So we'll see that naturally in this birefringent crystal example, directions appear where this metric degenerates. And then we want that in every tangent space exists a closed subset Sx, where the Finsler Lagrangian is 1, the signature of the L metric is Lorentzian, and the special sign of the Lorentzian metric in the signature of the metric is given by the sign of L. And then the Finsler function of such a space-time is a derived object and defines the length of curves. So the main difference between other definitions of Finsler spacetimes is that we have an R homogeneous Finsler Lagrangian from which we start, and that we have this rather, not so straightforward condition here on the existence of a certain subset in the tangent spaces. So why do we need them? So the homogeneity ensures the parametrization invariant of this length measure for curves. This we need to have our geometric clocks. This non-degeneracy condition, that we want non-degeneracy at least somewhere, ensures the existence of the geometry, and in particular we want that along the null directions of the space-time this GL is non-degenerate nearly everywhere. Then this condition will single out a subset, a shell of the non-compact indicatrix of such a Finsler Lagrangian, which we identify as shell of unit normalized stable observer directions. So this basically defines our stable time-like directions. And then finally, this is a mathematical realization of an observer's clock. So some remarks on this definition, how it's related to other definitions in the literature. Okay, I forget to cross this out. When we look for the two homogeneous case here, we are crossing this nearly everywhere out, but just taking a non-degeneracy of the Finsler, this L metric everywhere, then we are back to Beam's indefinite Finsler spaces. And then there exists a definition of conic Finsler spaces by Yavayoles and Sanchez, and when we compare the set of conic Finsler spacetimes with the set of Finsler spacetimes defined like this, then we find that they are not overlapping. For example, the Randers metric is a conic Finsler spacetime, but not a Finsler spacetime according to this definition, while these mth order polynomials, which I would like to include in this definition, as far as I understand, are not conic Finsler spacetimes, but are included in this definition. And in particular, it would be nice to merge this, to have an even more general class, because I think from physics, these examples are very, very interesting and appear quite naturally. Okay, then this closed shell I want in each tangent spaces, which shall identify my observers, is best explained again on the example of the bimetric Finsler Lagrangian. So for such a Lagrangian, as we had on the previous, some previous slides, we find the null structure of the two metrics, and in between the cones, the null cones of the metrics, we find a set where the L metric degenerates. That's unavoidable as far as I see. Simply it exists in these examples. Then we can look at the sign of L to classify observers. We may say, okay, all tangent directions for which L is larger or smaller than 1 are our time-like directions. This does not work in such examples because the sign of L is the same for the vectors which are time-like with respect to both metrics and for the one which are space-like with respect to both those metrics. So we need a refined classification of directions for for directions in the tangent space. And that's why we came up with the following. We look at the signature of the L metric, which is plus, minus, minus in this part of the tangent spaces. Here it degenerates, and here it flips sign. So there is a sign flip. So the signature is not constant. And then we can look at the indicatrix, and you have to imagine this picture mirrored. It just showed the details in this part to make it visible at all. So we look at the indicatrix of this Finsler function, which are these red slides here. Then we look which match this condition. So where does the sign of the special sign in the signature of the Finsler Lagrangian metric match the sign of L, that is here and here. And then we find that these sets are not closed since they are intersected by this degeneracy set. And we find this shell as X, which is exactly giving the normalized stable observers we had in the, which exist in this, when you look at physical processes in media. And this is why this, we think that every Finsler Lagrangian which satisfies this axiom is viable for physics. And making stronger claims may exclude such interesting examples.
We also have, in the past, another...
Sorry, I'm not precise enough. You have here another shell as X, and you must identify one for future and past pointing directions.
And it has no reason to be symmetrical.
No. That's just for the example I chose here. You can also tilt these cones against each other. So that's just, I chose a centered example. Actually, what you really have in crystals are not necessarily centered examples. They may overlap the cones.
And in particular, you don't have reversibility.
Here not. I, in principle, would like to have reversibility. I didn't include it here because the slide is already full. But in principle, I want it so that the length, the time an observer measures is, so to say, it doesn't matter if I go from past to future or future and past. Yeah, exactly. And what you have in crystals, what you often have are, in realistic crystals, you have such examples where you have a cone structure. Let's say you may have one metric, one cone, and you may have another cone. Maybe we draw it like this. Something like this, sorry, we have another cone. And then the relevant cone where we find the time-like, the stable observers is the one which is the intersection of the two cones. Yeah, so such situations are way more often. And then you have a degeneracy of the L metric also along the null structure, namely exactly where the cones intersect. So this is what you find in realistic crystals.
Do you need also some assumption on the dependence of this S on the point X?
Since L is smooth, I also want it to be smooth, so not jumping or so, yeah. But I think I don't need to assume it if I assume L is smooth. Okay, and this way we ensure the existence of a causal structure and a precise notion of observer directions. Now, yeah.
Can you go? Yeah. So if you have not a bimetric but a trimetric?
Yeah, then you have 3 cones, and you can look. Then this SX would be the. If you have a 3rd cone here, it would be the most inner cone.
But it does not. I mean, this S cannot appear on the intersection of further out, yeah? Because it seems that your argument you've given here depends on that you only have 2 cones intersecting.
I hope not. But I think not, because then I guess when you have 3 metrics, you get another degeneracy set here, which then would again single out you this one closed connected component. That's why we have this formulation in terms of closed components. If we have time, I can give you a bit different classification later. What it has to do with is that we want that L is a hyperbolic polynomial actually, and then these are kind of the hyperbolicity vectors. Yeah, comes from PDE theory when you study the initial value problem and so on. This is one way how this emerges. Okay, now observers. So we identified these directions of these stable observer directions. So an observer is a curve with tangent in this observer direction. Here it is. Then the time an observer measures between 2 events happening here and here is given by the length of the curve, which is defined in terms of the Finsler Lagrangian, which induces a Finsler function. Then we can look at the spatial directions. So observers locally make a space-time split, and relativity is exactly the point that this space-time split is connected to an observer. So it's different for each observer and dependent on an observer's state of motion relative to each other. And what one finds is that spatial directions can be defined as the set of vectors which are annihilated by the differential of the Finsler Lagrangian at the position of an observer. Also coming from PDE theory, this is exactly this condition which gives you the initial data surface of a hyperbolic PDE. Yeah, if this L is a dual of a dispersion relation. And then the question is, how does an observer measure spatial length? So these definitions are intrinsic to the definition of Finsler spacetimes. Every other measurement must be derived from an in principle doable experiment, and spatial length can be nicely determined by a so-called radar experiment. So what do? An observer carries a rod around and mounts a mirror at the end. Then at some point, the observer emits a light ray, which gets reflected at the end of the rod, which then propagates back to the observer, and the observer measures the time which passes from the emission to the receiving of the reflected light ray. And then the observer can associate a number to this length, to the spatial object, which is proportional to this propagation time. If you want to convert the units, so this is a measurement of time. If you want to convert it into units of length, you need a proportionality constant, which is maybe the constant speed of light. But if we don't have a constant speed of light, it's a bit... Oh yeah, it's 1. But if it's not constant, because it's we don't haven't said yet anything about how an observer measures velocities, and the measurement of velocity is connected to the measurement of length. So this is really a bit tricky to define these physical notions, because when you have when you have Riemannian geometry, pseudo-Riemannian geometry, then this all comes together easily. How this works here, if your operational measurement of velocity, it must be influenced by the geometric structure you have, and so if there are possibilities that some deviations from special or general relativity cancel each other, because you also need a refined definition of an observer's measurement. This is not yet systematically investigated. We will see an example in 2 slides. So on a flat Finsler spacetime, I call a Finsler spacetime flat. If the Finsler Lagrangian is not depending on the base manifold coordinates, we can imagine this radar experiment like in a vector space. Yeah, you have a light-like curve, you have a time-like curve, you have the reflection point, and then the condition that this is a light-like curve and this is a light-like curve is given by this, where we add simply here these curves together to obtain the outgoing light ray and the incoming light ray. And then this length the observer associates to this rod is given by the sum of these coefficients. And when one does it, for example, for a perturbation of the special relativistic Finsler Lagrangian, here we take the square because we wanted to investigate a 4th order polynomial, then you get such an expression which looks quite ugly. So to 0th order, we really see the special relativistic result, the length an observer's measure for a spatial direction is given by the metric norm of this vector. But you get a very complicated first order correction to that. And if they may be able to eat up each other for certain choices of these perturbations, needs to be investigated. So these B's are very kind of complicated functions in terms of these perturbations. Okay, and so then an observer's time and space directions and the measurement of time are determined by the definition of Finsler spacetimes and by geometrically intrinsically defined, while further observables must be derived from an operational procedure. Yeah? In particular, we see it's not simply here that we take the Finsler Lagrangian evaluated the Finsler norm of this spatial vector or something, which one may naively expect. This is simply not what coincides with the outcome of such an experiment. Okay, what's the time? Then finally, we want to discuss dynamics of Finsler spacetime, and we cooked up some action-based Finsler gravity equations from an action on the unit tangent bundle. So therefore, we need the building blocks of the geometry, since the gravitational dynamics are defined in terms of curvature tensors. So here we construct the Cartan nonlinear connection in terms of this Finsler Lagrangian. Its curvature given by the commutator of the horizontal basis vectors. And then we can define the canonical Finsler curvature scalar and the Finsler-Ricci tensor by taking the trace over these two indices here and contracting the last free slot with a direction. And what's nice is that everywhere where this induced Finsler function is differentiable, that this Cartan nonlinear connection coefficients can be equally derived in terms of the Finsler Lagrangian and in terms of the induced Finsler function. So in this way, we really think that the geometry formulated in terms of a Finsler Lagrangian extends the Finsler geometry of an equivalent Finsler function to the space where it's non-differentiable. Okay, we already heard that the Einstein equations determine the geometry of spacetime in general relativity, and now the Finsler generalizations fall basically in two classes. On the one hand, there are those which write formally similar equations on the tangent bundle, which are tensorial equations on the tangent bundle, which should determine the Finsler metric or this L metric. And examples in literature are the ones by Azanov, who used the curvature tensors of the Cartan linear connection and replaced this open y dependence by another vector field. Or Lee wrote down similar equations in terms of the Finsler-Ricci tensor and Finsler-Ricci scalar, where it's a bit open. I didn't completely understand what this energy momentum tensor then is. Then the other class are scalar equations on the tangent bundle, which shall determine scalar quantities on the tangent bundle. And there's the one by Rutz, which is derived from the geodesic deviation equation, and they are the ones which we derived by variation of an action on the unit tangent bundle with respect to the Finsler Lagrangian. And here we have the Finsler curvature ingredients, and this is the Burwald covariant derivative and the Landsberg tensor, and this is a so-called dynamical covariant derivative. I prefer these scalar equations, since the fundamental variables we use in Finsler geometry are scalar quantities, and when you have an action and do variation of an action with respect to your fundamental variables, you get an equation of similar type. What can be shown is that this equation by Rutz cannot be derived from an action, but one can perform a procedure called variational completion, which then shows that the variational completion of these equations are exactly our equations. That is similar when you compare it to the genesis of the Einstein equations, where Einstein first suggested an equation like this, just the Ricci tensor equal the energy momentum tensor. This is not complete, and also it can be shown it cannot be derived from variation. And then you get from the Einstein-Hilbert action, or also via this variational completion, the Einstein equation. Yeah, that is why we think this is the best suggestion for generalizations of the Einstein equations to Finsler geometry. I forgot this variational completion goes back to Nicoletta Voiko and Demeter Krupka by a paper in 2014 or 15. Forgot to enter the citation. So, and this is how this action looks like we use. So the unit tangent bundle is this set of unit vectors, all unit vectors measured with this Finsler Lagrangian, independent of their causal structure, causal properties. And then the action is given by this integral, where we have a suitable volume form on this unit tangent bundle. And when you do variation now with respect to L, you exactly get this equation.
That would be your Hilbert action.
Yeah, this is a generalization of the Einstein-Hilbert action, in my opinion. And there is, if you go to the positive definite case, it's you can even show that for a Riemannian metric you really can derive something like this, because you can then integrate out the y dependence and you get something like the Ricci scalar. Here we cannot perform the integral explicitly because the indicatrix is non-compact. Or at least, I don't know a method. It would be interesting to see if such a thing is possible.
How do you ensure convergence?
Yeah. That's a, yeah. So I think there's a general thing with action principles in physics. You can see them as distributions which act on some test functions with compact support and so on. It's not in detail investigated. When you do variation, you say you do variation with respect to perturbations of compact support, and you want that for every compact supported perturbation this is finite.
Okay, so you see this as a
infinite line in Euclidean geometry are still minimizer.
Yeah. So there are open questions how to do this mathematically precise, and I'm very interested to optimize the derivation of this action, also this formulation. Maybe one must take all compact subsets in this unit tangent bundle and then do variation, or there are some mathematical tricks. Okay, how long do I have? 5 minutes. Okay, then I come to conclusion and outlook. So, I hope I convinced you that these Finsler spacetimes realize the threefold rule of the geometry of spacetime. So, the causal structure is existing, so we know what are stable time-like observer directions by the existence of the shell as x. Then observers' time and space directions are determined by tangent vectors inside this shell as x and by the directions which are annihilated by the differential of the Finsler Lagrangian. The time measurement is given by the length of an observer's curve. It's a clock postulate, and the length measurement is given by a radar experiment. A notion of spatial length can be obtained by a radar experiment. And vacuum dynamics can be obtained from an action on the unit tangent bundle. And in particular, we include these important examples, which are polynomial Finsler Lagrangians, which describe the propagation of particles in media, and which can be derived from physical field equations. And maybe I take a short second to elaborate on this. So a physical field equation is a partial differential equation which shall be predictive. So it shall have a well-defined initial value problem. That one can ensure this by looking at the different terms of derivatives. So we have a partial differential equation. Oops. So we have a partial differential operator acting on some field, which can be written plus lower order derivative terms. And then this highest order derivative term is a so-called principal symbol, which determines the causal behavior of this partial differential equation. And this must be when you replace the partial derivatives by wave covectors doing the geometric optic limit. This must be a hyperbolic polynomial. And this hyperbolic polynomial then is such a dispersion relation which we had on the cotangent bundle of the spacetime. And in order to be then also quantizable, this hyperbolic polynomial must, on the cotangent bundle, must possess an algebraic dual, which is also a hyperbolic polynomial, which would be on our Finsler Lagrangian as mth order polynomial. So this is how you really get from physical field, from fundamental physical field theories, how you reach such Finsler Lagrangians. And you can start this reasoning with Maxwell electrodynamics, from a modern point of view, arguing how you get from Maxwell electrodynamics to general relativity. Okay, and then some outlook. So, it would be interesting if we can discuss if we optimize this definition of Finsler Lagrangian, Finsler spacetimes, and find a definition which, so to say, unites all the definitions there are in the literature. It would be very interesting if we can agree on something or not, or classify exactly where the differences are, what are the problems. Then, from the physicist point of view, we want to calculate observables to find and classify viable Finsler Lagrangians. So we may look at a perturbation, first order perturbation, and calculate all sorts of observables we have, like shadows of black holes, which are derived from innermost circular photon orbits, gravitational redshift in cosmology and spherical symmetry, then the classical tests of special relativity, Michelson-Morley experiment, Ives Stilwell, Kennedy-Thorndike, lensing effect, rotation curves of galaxies, and so on, to get conditions on these first order perturbations beyond general relativity. so that we know what these need to satisfy to be viable. And then there's an interesting description, relativistic description of gases directly on the tangent bundle. Would be interesting to couple this directly to a Finsler geometry. And then something like the initial value problem of the Finsler gravity equations would be interesting. So are they predictive? Or are there further conditions needed to have predictive gravity equations? And with this, I thank you for your attention. And these are the papers on which this talk was based. Thank you.
Yeah, thank you for your talk. Your beautiful talk. Are there questions?
Do you have any solutions of these equations? They look rather complicated.
Yeah, they are. We have no non-perturbative solutions. We have perturbative solution of this type for n equal 2. And that is, for example, there exists a phenomenon called the flyby anomaly in the solar system. When satellites do a swing-by maneuver to gain velocity, there have been some which were faster afterwards than expected. And you can model such effects with a Finslerian geometry. But it's not really surprising because you have more degrees of freedom, you have more parameters to tweak. So that's just an example where you can have it. And no, we don't have, I don't have solutions. We are working on that. For some examples, for example, there exist these very special or very general relativity spacetimes, which are these Boguslavsky length measures. There exist some plane wave solutions, which Andrea found. And so for some simple situations, we can get some solutions, yeah.
Are there more questions? No? But then I might have a question.
Yeah.
Did you investigate the geodesic equation of these things? Especially if you have, like, I still see your picture there on the blackboard, where you have these light cones that are not contained in each other, yeah? Because, of course, the light-like geodesics, I would expect they stay inside this the shaded cone you drew.
No, the light-like geodesics are the one which run here on the null structure.
Yes.
And then you have some which run here, and you may also have some which run here, but they may then...
can they change the...
Yeah, they might decay here, so there's an energetically allowed process which we would expect to happen, that, like, consider an electron in some dielectric in some liquid.
The time-like one, that is... Yeah, okay, they can, like, they go...
They can decay and then proceed here by sending out a photon.
Okay, but they lose energy, yes.
They lose energy, yes. And this energy is carried away by a light ray.
No, I'm talking about geodesic, like really free-falling particles, or...
Yeah. I mean, you have your Finsler Lagrangian, which is your action, basically defines the action of your point particles, and this is your connection, and you get your geodesic spray by contracting this with a direction, and then you have your geodesic equation of the Cartan nonlinear connection.
Do you know if this is a geodesic variational equation?
Yes, it is.
So if you write down a variation of the energy, yeah?
Variation of, basically of the R's power of this.
Like the energy.
Exactly. Exactly, that's the idea.
Well, okay, then the time-like ones I would expect they stay inside the cones, but the light-like ones I'm not so sure, because you have these like two intersecting hypersurface, and then it's kind of...
The question is the light. So the lights are distinguished by their polarization. So if they can choose if they can change polarization, then if they so the question would be if they spontaneously do it, or if they...
Well, they can only do it at the intersection of
exactly. If they do it, yes.
Okay.
So there I would need to check the literature on these crystals again. I think this is known for physics in media. Yeah.
Okay. Thank you. More questions? If not, then we'll thank the speaker again.
Thank you.
And we will restart at 10 minutes past 4, yeah?